drove, navigated for a mobile mesonet, and really an incredible experience. Although I think we could have seen more tornadoes than we actually did see, but that's another story. And then after Vortex, I worked at the National Weather Service as a researcher for about 8 years. Really an incredible experience. Did end up moving away from Oklahoma, not because I didn't love it, but because I met and married my wife, who is from Tennessee, and shifted gears a little bit. And now I'm doing a career in supply chain management, and that's been a very rewarding career, but I still enjoy tornadoes and forecasting, and that's what we'll be talking about tonight. So here are just a few of the tornadoes that I've seen through, I guess, almost 2-decade career. Top left is a tornado that I saw near Tipton, Oklahoma in 2011 in November of all times. A very powerful outbreak of tornadoes, including an F4 there with the tornado before. Another view at top center of the May 24, 2016 Dodge City outbreak. I believe that was the, I want to say it was the first tornado, but kind of in the later stages of its lifetime. Very powerful tornado, incredible debris field with that one. To the right, you see a multiple vortex that I was able to see down near Tushka, Oklahoma. Came in behind the storm, went through the Hook Echo, and was greeted by this view of a multiple vortex tornado, very large subvortices rotating around each other. Very incredible experience. However, we were rewarded with that view, but also some golf ball to baseball sized hailstones in the RFD on the backside. So I actually busted out our windshield, and that was, I think, the first of 2 times that I lost my windshield in a tornadic thunderstorm. And then you can see Roselle. Everyone knows Roselle, 2013, an absolutely incredible tornado. I was also able to see the Moore tornado in 2013, which was a different type of tornado, very ominous, very loud. This is about 2 miles away there in the center, and that was a very just a sobering experience. And then May 24th, 2011, I saw a bunch of violent tornadoes in central Oklahoma. That was one of the bigger outbreaks that we had during that decade. And you may be familiar with the bottom left there, the Mulvane tornado. That was taken with a 8mm video camera, but one of the most beautiful tornadoes I've ever seen. Just an awesome picture there with that Eric Wynn took. I don't know if you remember him, though, the late Eric Wynn, just an amazing chaser, an amazing photographer, got a great shot of that. You see Hallam to the right of that, and then finally you see the tornado from May 9th, 2016, just near Wynnewood. So anyway, with that, I just wanted to give you kind of a background of my chasing career. I don't want to go into too much detail, but the meat and potatoes of what I wanted to talk about is sort of an introduction to the talk, what the motivation is for the presentation, and also go into the supercell ingredients, moisture instability, wind shear, and lift, and then finally to put that all together. And for most of you, I'm sure this will be just a refresher, as many of you chased storms already, but for those of you who don't, this may be new, and hopefully it's at a pace that can be absorbed. I'm going to try to go slow enough to give you some good information. So just as an introduction, so here are the tornadoes from 1958 to 2019. And typically I would show this graphic maybe as an illustration of Tornado Alley, but as you can see, really there is no such thing as Tornado Alley east of the Continental Divide. There's so many tornadoes all across the United States. It starts to taper off as you go into the Northeast, and where I live, unfortunately, or I guess fortunately, depending on your perspective. But really, the thing I want to draw to your attention here is what causes these as sort of an antecedent to what comes before, and that is supercell thunderstorms. Supercell thunderstorms are responsible for 80% of tornadoes. And this is obvious to most of you. But the reason I draw this out is that I want to talk about ingredients for supercell thunderstorms as opposed to anything else, that will help you to identify where areas of favorable conditions might come together for tornadoes. This supercell, of course, as many of you know, is the El Reno circulation from May 31st, 2013, which many of you had some tough experiences with, including myself. A 2.5 mile wide tornado there, unfortunately, did kill some of our own. And so hopefully we can all stay safe out there this spring. But these forecasting tips will hopefully get you closer to these type of storms. Some other facts about it, again, supercells are rotating thunderstorms. That is essentially the definition. They can last for hours. As you saw with I believe it was December 10th, the date of the Quad State tornado, they can last for hours. I think that one lasted somewhere between 8 and 10 hours, somewhere along that line. And they're responsible for almost all EF4 and 5 type tornadoes. So the violent tornadoes that can wipe houses off their foundations, that's what produces them. And they produce almost all of the giant hail as well. So that would be greater than 4 inches in diameter. In fact, this particular thunderstorm produced the record for hail in Oklahoma. I believe it was somewhere around 6 inches in diameter there in El Reno proper. And that is going to be trouble if you encounter that. So without further ado, we can get into some of the ingredients for that. So again, for supercells, you need essentially 4 ingredients, and that's the way I'm going to approach this tonight, talking about moisture, talking about instability, wind shear, and finally lift. So let's get into it with the topic of moisture. So the first thing you need to think about when you think about moisture is that you need to get moisture into the plains or wherever that tornado event may occur. And that moisture does not originate obviously on the plains. The plains are dry, but it originates in the Gulf of Mexico and the Caribbean. And the process that moves this moisture to the plains is called advection. So advection is just basically any property that is moved by the wind. That could be moisture, that could be temperature, that could be vorticity, that could be a pencil, that could be a pen. Anything that's moved by the wind is advection. And then the primary driver for moisture advection is called downsloping. And that's what the process I want to open up with, because that's really the stage setter for all that I'm about to talk about. And to really look at this process, I recommend using the 500 millibar, 850 millibar in surface charts. So here's a graphic that I came up with a little bit ago. This actually shows the jet stream axis, essentially the strongest jet stream winds on May 31st, 2013, the date of the El Reno tornado. And this would be essentially representative of the 500 millibar winds in that situation. So the way I want to illustrate the principle of downsloping is by to take a slice right through the jet stream there, especially as you look from, say, Denver down to Oklahoma City. How are we going to get that moisture from the Gulf of Mexico up to the plains? And so here's a graphic that I created to show kind of if you take that slice, kind of a vertical slice, and you go from the Rocky Mountains to the left down to say maybe Oklahoma City to the right, that's what we're looking at, Denver kind of towards the center of the screen. So in that case, with the jet stream, the winds would be coming from the left to the right over the Rocky Mountains. And of course, there are no vacuums in the atmosphere. So the air actually moves over the Rocky Mountains, and it goes through a process of compressional warming. One thing to note, obviously, if you've been to the Rockies, you know that if you're climbing the mountains or running up there, the air is less dense. There's less air at the top of the mountains than there is at the bottom. So as you're moving from less dense to more dense, you're kind of compacting that air a little bit more. So those air molecules are getting more and more dense. And as they're having more interactions, that's a compressional effect, which creates warming. And so at the base of the mountains, in the lee of the mountains is what they say, that's where we see a lot of warming. And actually, interestingly enough, this process also happens in the wintertime. The Chinook wind, if you're familiar, snow eater, as it comes down the mountains, it warms. And so you can have a massive snowstorm. And then, not a few days later, when you get these westerly winds over the Rocky Mountains, you end up with snow that melts rather quickly. But warm air, as you know, tends to rise. And this is a way that I want to illustrate that with the hot air balloon is probably the best way to describe it. So in the hot air balloon, you have warm, light air surrounded by relatively cool, heavier air. And so the reason I draw this out is because if you have warm, light air, it tends to want to rise due to the pressure gradient force. Now, the pressure gradient force goes from areas of high pressure to low pressure. So you want to rise in general. And then in gravity takes that in the other direction. So if you have a little bit more pressure gradient force in the middle, or in the, if you have a little bit more pressure gradient force than you have gravity, you end up having a net upward force known as buoyancy. So in this case, the air at the base of the mountains tends to also rise in addition to warming. So you see that that warming process, which is a cooling process as well, because so you warm as you go down the mountains, and as that air rises, it cools. And so you kind of develop essentially a low pressure there at the lee of the mountains. And this is what is known as a lee cyclone, which is just a low pressure, elongated low pressure in the eastern side of the Rocky Mountains. And air tends to rush in from basically all around to fill that low. So you have air going down the mountains, and you have air coming in from the east and southeast. And that process, you can see here on this sort of plan view, that low pressure area in the lee of the mountains. And then you have winds that come in to fill that low pressure from this east and southeast. And then you kind of superimpose the moisture that was in the Gulf of Mexico, and it actually begins to move towards that low pressure. And so that's the process of advection that really brings in this moisture that sets the stage for a lot of other things associated with severe weather. And so that's really what that would look like in that sliced view. You can see the moist layer coming in. And at the same time, you want to be looking for high dew points. So in addition to just moisture in general, obviously, the higher the dew point, the more energy it has in it for thunderstorms. Lots of energy available for latent heat release in particular. And I just as sort of a rule of thumb, high is relative. It depends on the time of year and the elevation. Upper 50s dew points Fahrenheit is pretty good in March, but not so good in May. If you're in, sort of like in the Norman, Oklahoma, or Wichita, Kansas area. And that's the reason that upper 50s in March is a little bit better is, you've got cooler temperatures typically in the early part of the spring. So that creates a lot more temperature differential between the surface and what's above that. But in almost any time of year, if you get upper 50s in the high plains, that's actually pretty good. And we can see that here in a little while when we go over the topic of skew-Ts. And you can see why that's the case. But for high dew points, obviously, you want to use a surface map. And so just to kind of reorient you for what to look for in a surface map, this is a typical station plot here, where the primary thing I want to draw your attention to is the wind here. You can see in this case, the wind barb points to the southeast. So that means a wind from the northwest to the southeast at about 15 knots. Then you have the temperature here in the top left, the weather conditions, and then the dew point temperatures. So those are the primary things that you'll want to be looking for: the wind, the temperature, and the dew point. And this will give you some guidance as to what those local weather conditions are where the severe weather may occur. And in terms of flag values, just as a reorientation, this goes from calm all the way to 145 knots. And if you don't know what a knot is, it's about a mile per hour. It's a little over a mile per hour. I think it's 1.15 miles per hour equals 1 mile per hour, or 1 knot. So it's you just basically multiply knots by 1.15 and you got your miles per hour. So basically, you can see the smaller flags correspond to about 10 knots. And then the big flags are the ones with the triangles, about 50 knots. So that's really all you need to know, especially as you start to look at those upper air charts. Okay. So I wanted to start with looking at the surface plot for May 24th, 2011. You may have chased this. This was a big, significant, typical classic plains outbreak. Tornadoes from Texas all the way up to Kansas, with the primary focus of that violent tornado outbreak in central Oklahoma, where I believe we had I think officially 3 violent tornadoes, including some high-end EF4s and one EF5 near El Reno. And here was the surface chart around that time. This was around 3 p.m. So I believe at this point, we already had a tornadic thunderstorm either in progress or almost becoming tornadic kind of in the southwest Oklahoma area. And I know we had one in northwest Oklahoma at that time. And at the time I was playing monkey in the middle and chasing the middle supercell, which is, by the way, not the greatest idea in the world. We did miss the early tornadoes with that, but caught up with the storms later near El Reno. But what I want to draw your attention to is just the classic look of what you see here with a low pressure system right here up in southwest Kansas, northwestern Oklahoma. Everything's kind of going toward that, like towards the sink drain. And one thing that I'll note about the winds is that they're generally from the south-southeast, which is pretty much what you want to see. In the plains, you're looking for south-southeast or southeast winds. And if you get them to the east-southeast, that's even better. Dew points here in the 70s, so very rich, very juicy Gulf or even Caribbean moisture. Here's another case for surface moisture when you're looking at March 28, 2007, another big outbreak. And it was a little different in terms of how that moisture looked. And I want to draw your attention to this because not every big outbreak is going to feature surface dew points in the 70s. This particular case, it was actually in the high plains. So I talked about how in the high plains, you actually don't need as much moisture. You get more bang for your buck for your moisture in the high plains. And this one produced many tornadoes. I saw some down near McLean, Texas that evening, and it was quite an event. That was the look of the surface map at that point. So again, you see the southeasterly winds, and actually you can see that they're a little more southeasterly than they are in the May 24th, 2011 view. We call that backed. So anytime the winds move from southerly, from the south to southeasterly, that is the process is called backing. So when people talk about backed winds, they're talking about more southeasterly winds. In this case, you see backed winds pretty much across the entire plains. So definitely good for the low level turning that you'd want to see for severe thunderstorm development, including tornadoes. But you can look at what was going on in the Texas Panhandle at that time. Upper 50s dew points, low 60s. This is not particularly impressive during the month of May, and particularly in the Oklahoma City area. But on the plains at the end of March, this was good juice for tornadoes. And that outbreak was one of the more significant ones we had in the early 2000s. Another key part of moisture, the topic of moisture, is deep moisture. So it's not enough to just have moisture that has high magnitude. As many of you know, sometimes you can get dew points that in the morning, it'll be 65 degrees, 70 degrees even, but that will only be skin deep type of moisture. So above that layer of moisture near the surface, you have right above that a lot of dry air. And as the sun comes out and heats the ground and you start warming the ground and you start developing thermals, those thermals begin to mix that air. And that process of mixing will take those dew points that were really high at the surface and kind of dilute the moisture quality. So why you want deep moisture is you want to avoid that turbulent mixing, because that will reduce the instability if you have that some very shallow moisture. And so the way you want to look at the moisture depth is to look at the skew-T log P. And so just to orient you with the skew-T log P, this is a chart that really measures the change in temperature, humidity, and really just wind speed as you go up through the atmosphere. So I want to orient you with the x-axis. That's a lot of different things. I'll show you what those things are, but including temperature and mixing ratio. And we'll also have dry adiabats and moist adiabats. But on the vertical axis, this is the primary thing, and this is where the log P comes in. It's a log of pressure. So the pressure coordinate is very tight near the surface, and then kind of those differentials, the delta between 500 and 450, for example, is much bigger than 950 and 900. So that's where the log P comes into play. But the isotherms follow these lines. So you can see right here, that's the 10 degrees Celsius isotherm. And that just shows a line of constant temperature. That's what isotherm means, constant temperature. And this right here, so if you look at this little orange line that kind of goes from lower right to upper left, those are the dry adiabats. So that means that's the temperature that if no moisture is involved and you're just rising, you're taking a parcel of air, essentially a bubble of air, and you're moving it on up in the atmosphere, that's the rate at which it will cool if it's dry. So in this case, it'll be about 9.8 Celsius per kilometer. And that's the case universally with the temperature decrease. That's dry adiabatic lapse rate. The moist adiabat is following this other line here, these sort of green lines going from the bottom to maybe the top left. And this cools a different rate. It's a little shallower, so it may be somewhere between 4 and say 6.5 Celsius per kilometer, depending on a number of factors. And then finally, constant mixing ratio, these little dotted green lines that go from bottom left to top right. Those just indicate how much water vapor there is for every kilogram of dry air. So, for example, 12 grams per kilogram, that's a pretty decent mixing ratio. During, some of the more intense tornadic events in, say, June, you might get 16 grams per kilogram. So just to orient you with the values there. So with that, here's a observed sounding from Amarillo. So this was taken during that March 28th, 2007 outbreak with those tornadoes out in the Amarillo area through western Kansas and into Nebraska. In this case, it's arguable where the top of that boundary layer is, that moisture layer. But in this case, I'd say it's about 100 millibars deep of moisture. So it's not particularly deep, which is not surprising given that's kind of late March. Typically the boundary or the moisture layer gets more deep with time as that moisture improves through, say, April and May and into June. And then, so for the example of the May 24th, 2011 outbreak, that had incredibly deep moisture. In this case, this is the Fort Worth sounding, so a little bit further south of the outbreak center, but you can see very, very deep moisture on the order of about 250 millibars deep. So whenever you see that kind of depth of moisture in the upstream sounding, so say you're thinking, okay, golly, I'm wondering how quality this moisture is going to be coming into Oklahoma or Kansas tomorrow, you'd want to say, if you're in Oklahoma looking for the next day in central Oklahoma, you'd be thinking, okay, what does the moisture look like in Corpus Christi down in Texas? And as that moves on up into the Oklahoma area, what is that going to look like? And so you want to look for that deep moisture. Another important factor is source region. So early in the storm season, it is really helpful to identify where that moisture is sourced from. Even if there is southerly flow over the Gulf, sometimes you might not get that quality of moisture that you want. Now, later in the season, it doesn't typically matter terribly much about, especially as you head into late May into early June, where that moisture is going to come from. It's pretty much almost always there. So you're more looking at kinematics, you're looking for shear rather than for moisture. But early in the season, this matters quite a lot. And to assess source region, you want to look at a surface map. So I just wanted to point this particular case out as an example of why source region matters. So this is March 23rd at probably 6 or 7 p.m. Central Time. And there was a potential for severe thunderstorms and tornadoes on March 27th. And when we looked at the models at that time, I was getting very excited seeing shortwave coming in, shortwave trough with associated increases in storm relative helicity, et cetera. And in fact, the wind shear profiles looked like they were going to be almost ideal. But the real problem manifested in terms of the moisture. And if I had been more aware of this fact about source region, I might have looked and seen the surface charts and seen, okay, gosh, if we take a trajectory from where this moisture is coming from in central Oklahoma, you see this good southerly flow over Oklahoma. That's what you want to see over Texas. But where is it originating? Well, if you actually draw a line backwards to see its origination point, and you see that it's actually originating over this kind of northeast Florida, eastern Florida area. And if you look at those dew point temperatures, 47, 50, 51. So that's pretty low quality moisture. And so if you actually advance this in time to the next day, the next night, so 24 hours later, you can see there's not a whole lot of improvement in the moisture in Oklahoma. You see 60, 63, but as time goes on, it gets a little bit better, 63, 64. But again, source region's not great. And by the time of the outbreak, or not the outbreak, but the supercell threat on March 27th, you can actually see the supercells in this composite radar. The dew point was still about 60 degrees. And so what the upshot is, we had multiple supercells rotating, spinning like a top, but because the moisture just wasn't really there for tornadoes, we only saw one, I think, significant tornado, or I don't even know if it was significant, but it's a substantial tornado near Arnett, Oklahoma. And beyond that, it was a pretty benign event. And you can see that here, how that shaped out. In terms of supercell ingredients, we've already covered moisture. And so we can move on to instability. So instability, going back to that slice through that we saw of the Rocky Mountains with the moist layer. So if you can imagine, as that air is moving down over the Rocky Mountains, it's also warming at the dry adiabatic lapse rate as it's going down. And so what you end up with is what they call an elevated mix layer. So what that means is that the air is relatively well mixed through here. So it's fairly homogeneous. It follows that dry adiabatic lapse rate. It's relatively warm on the bottom end of that layer and relatively cool on the top. So if the air is really warm and it moves over that moist layer, this is what you might think of as the capping inversion. And the strength of that will, in many cases, determine whether or not you get storms and how many. So if we take a slice right through this particular part of the elevated mixed layer, say at Oklahoma City, I want to give you a sense of what that skew T log P might look like. And this is not exact at all, just sort of idealized. So let's say at the surface, you have surface temperature in that little red dot area. Surface temperature might be roughly about 30 degrees. So in the 80s, probably. And then in the green dot is the dew point temperature. That would be close to 70 degrees, let's say, at Oklahoma City. And so what you want to do here is when you think about a parcel of air that's rising, that's being forced up, what pattern is it going to follow? And the first thing you want to do is for that dew point temperature, you want to follow those mixing ratio lines until it intersects with the temperature following the dry adiabatic lapse rate. And that point where they intersect is where the temperature cools to the dew point temperature. And that is the point at which condensation occurs. And then once condensation occurs, it releases latent heat. And latent heat is a warming process. So then the environment will be cooler than the cloud. So here's the cloud. The cloud is going to follow the moist adiabatic lapse rate in this case. So it's going to cool at this kind of shallower rate relative to the environment. Maybe say that the entire environment is dry adiabatic. This is almost never going to happen, but just for illustrative purposes, you can see that there's a big difference between the temperature of the cloud, the moist adiabat, and the temperature of the environment, the dry adiabat. So why is that important? Well, this is a nice image to show that process of condensation and the importance in terms of latent heat release. So I want you to focus in this particular image on the process of going from vapor to liquid. That process going from vapor to liquid actually releases energy to the environment. So you're actually the vapor by being converted to liquid, by cooling and converting to liquid, it releases heat to the environment. So that cloud's going to be warmer and then everything else around it. And so then we go back to the hot air balloon illustration. So, that cloud as it's condensing is like the hot air balloon. So you can think of the cloud like acting like a hot air balloon relative to the environment, which is relatively cool. So you're going to have a net upward force. And so if you kind of think about it, that difference between the moist adiabat and the dry adiabat is actually the convective available potential energy. So that's just the energy that the environment, if air can be lifted to this point, then then it will be able to tap into that potential energy between what the cloud temperature would be and what the environment would be around it. Okay, so here's an idealized temperature profile. So it's pretty typical looking temperature profile, perhaps. You've got dew point temperature, probably again near 7 degrees Fahrenheit, 20 C, and it's following that constant mixing ratio. And that point where it intersects is the point where the temperature of the actual cloud compared to the environment is going to follow the moist adiabat. And then, of course, the environment will follow this red line here, the temperature profile. And then we've talked about the CAPE, which is the difference between those. It turns out that the intersection point between that constant mixing ratio line and the dry adiabatic lapse rate, as the surface temperature follows that dry adiabat up to where it intersects with that mixing ratio, is known as the lifting condensation level. And then it follows that moist adiabat up to the level of free convection. So this is important because once it gets up to the lifting condensation level, you'll notice that the parcel temperature, or what you could call the hot air balloon temperature, is actually relatively cooler than the environment. Notice that the actual environmental temperature is quite a bit warmer in this case. So what that means is if the hot air balloon is not as hot as the area around it, then it can't rise any further. And that is actually the capping inversion, is what you're seeing, that layer here where the temperature is actually relatively warm compared to that moist adiabat. And that's convective inhibition. So taken all together, this process of having moisture come up through advection, and then the elevated mixed layer coming in from the west, you can kind of see the jet stream in this plan view, you see the advection occurring, and the moisture starting to enter the plains. At the same time, you start to get this westerly wind that creates this elevated mixed layer, which then, if you notice the crossover between that moist air and that dry air above it, that is the unstable area. And this is from May 31st, 2013, kind of, again, an idealized view of what that looked like. So you can really see that when, you can see Storm Prediction Center or somebody else referring to the elevated mixed layer, that's what they mean. It's really that potential for instability as that air in the middle level of the atmosphere advects or is moved by the wind over the plains. More often than not, that elevated mixed layer doesn't make it too far to the east, but occasionally you can see very, very significant events like April 27th, 2011, where that air will actually end up over the southeast. In terms of instability, steep lapse rates, mid-level lapse rates from 700 to 500, your rule of thumb is you want to see at least 7 Celsius per kilometer. That's what you're looking for. There's a statement that I've always remembered. Ryan Jewell at the Storm Prediction Center always said, lapse rates above 8, tornadoes will be great. I don't think he necessarily coined that, but I always remember him saying that. So it's something to keep in mind. You see 8C per km or greater, those are some very good lapse rates. When you're looking at the May 24th, 2011 outbreak with the El Reno tornado, Goldsby, Kreiner area, that tornadic outbreak was preceded by this elevated mixed layer. And you can see how strong that elevated mixed layer was. So creating that potential for very strong instability. Instability on the whole is the integration, or CAPE in this case, is the integration of total positive instability, that purple area, that shading that I was talking about, and that's in joules per kilogram. And to maximize it, you need a combination of surface temps and dew point temperatures and mid-level lapse rates. So we'll look at that here in a second on how you might increase the CAPE. Some rules of thumb in March, generally in the plains, you're looking at greater than 1,000 joules per kilogram. That's not always the case. These just very loose rules of thumbs that I considered. In April, maybe 2,000 joules per kilogram. In May, anything above 2,500 is pretty good. But in general, that's what I would be looking for. So here's the idealized sounding that I put together. And maybe in this original SKU-T, you decrease the lapse rate. So in this case, I'm actually decreasing the CAPE. So you can see that the environmental temperature actually warms. If you had some warming in the mid levels of the atmosphere, that actually reduce your CAPE. So that'd be the opposite of what you wanted. So That's why cooling mid-level temperatures is actually relatively helpful for developing CAPE. So another way you might adjust your CAPE would be from the temperature standpoint. So let's say you increase your temperature by an obscene amount and you're near 100 degrees. This would be a nuclear kind of CAPE situation. It would erode that cap and then really increase the CAPE. By the way, I haven't gone all the way up to the top of this chart, but where these the red line and the green line intersect again way up in the atmosphere, that would be known as the equilibrium level. And so that's the tropopause, and that's where basically the storm flatlines. That's where the anvil is. But if you're developing really strong updrafts, you might overshoot that, and so you could get an overshoot maybe 10,000 feet above that anvil layer. Another thing to consider with instabilities, surface heating. This is, I think, a pretty important one to consider. It's not always necessary, particularly in the Southeast, where it tends to be higher moisture because of its proximity to the Gulf of Mexico. You might not need as much surface heating, but I think in the plains, to get a tornado, you do really need that significant vertical motion, and that is certainly aided by surface heating. Can achieve that through strong rotation. I've seen cases where basically the surfaces have cooled, the surface has cooled, and you're not really seeing a lot of CAPE, and maybe even a lot of inhibition, a lot of negative buoyancy to prevent tornadoes, or to prevent supercells even, but still producing tornadoes through some dynamic, what they call pressure perturbations. But anyway, you can see this, you can achieve this through strong heating, that strong vertical motion that you need for tornadoes. And the best way I think to see that process of surface heating is to observe when cloud streets go away on satellite. So this is just an example that I remember from 2005, where there was an outflow boundary. I believe it was kind of in that Childress area, and actually you can kind of see pretty cool outflow area all along western North Texas. And then heading into the Texas Panhandle, you can see these kind of puffy clouds moving away from sort of the cloud streets, say near Aspermont, to more of the puffy clouds out towards Lubbock. And this was actually a day when there was some pretty strong tornadoes near Jayton, Texas. And you can see those reports there on June 12, 2005. And again, instability, convective inhibition, that's just the integration of the total negative instability in joules per kilogram. I would say some can be helpful, but you don't want overly much. Rule of thumb, you probably would want less than 50 joules per kilogram. Really depends on the situation. So again, it's a rule of thumb. In the Southeast, sometimes you have those open warm sector storms where you really don't want too much convective inhibition. So you want the storms to develop freely. In the plains, if you have that same situation with zero convective inhibition, sometimes you get too many storms and you get a squall line. So just something to keep in mind. And obviously, if you have too much of it, then you may not get any storms at all. Looking at you, Iowa. All right, here's another look at the convective inhibition. And here's a view of that from plan view on May 24, 2011. Again, that big outbreak in central Oklahoma and into Kansas. And you can see that at 3 p.m., this is 20Z, so about 3 p.m. that day, there was not any convective inhibition per the SPC's mesoanalysis. You can see a little bit of convective inhibition in eastern Oklahoma, but out there near the dry line, you can kind of see that with these CAPE sort of isolines. There was no inhibition out there. And so the storms formed, you got these massive thunderstorms out there, and they rotated for a good long time. But by about 6 p.m., you can see how this convective inhibition built in. We went from about maybe zero joules per kilogram to almost 100 joules per kilogram by 6 p.m. And this certainly increased as time went on. And so you actually saw, as time went on, particularly towards the 7 and 8 p.m. timeframe, the tornadic weather essentially ceased. So it was kind of an early event. So that's a helpful illustration of how convective inhibition can be sort of deleterious or works against your potential for tornadoes. this was an example of a tornado that happened in Kansas. This is northern Kansas. I'm just showing you the path of this to illustrate that sometimes you can have really intense convective inhibition and still get a really long track tornado. In fact, there was a tornado after this one. I was out there with the Doppler on wheels in 2008, and this tornado went well after dark. I think probably to about, not this particular tornado, but the one after went to probably 10:30 at night on into Nebraska. But this was actually, 9 p.m., about the time of the Jewel, Kansas tornado. And you can see how amazingly powerful that convective inhibition is towards what you would expect. You'd expect something closer to 0 or maybe 50 joules per kilogram to continue with that tornadic thunderstorm. But turns out that if your thunderstorm is already rotating, really the truth is that you can keep that tornado going for a long time if the rotation is strong enough. And so that is the case for that. And so now that we've gone through those ingredients, I'm hopeful that I'm getting on time here. And if I'm going past time, Eric, give me a call. I can't hear you guys, so just let me know. Wind shear is the next ingredient. And so let's look at that. So again, May 31st, 2013, here's sort of the chart that I came up with based upon the surface chart, just so you can see it a little bit better. Anything in the green is dew points greater than 70 Fahrenheit, so very juicy air, what you would want to see for a tornado event. El Reno is the little star you see west of central Oklahoma. And then you can see the wind vectors at the surface. Obviously, you've got that backing that I was telling you about, southeasterly winds. That's something that if you look at, you see, okay, that looks like the area you might want to go. Maybe even a little bulge in the dry line here as the dry line comes in from the southwest. And so you might get some pretty strong convergence there. Above that, at 500 millibars, the jet wasn't overly strong. And so winds greater than 40 knots are highlighted here with those blue vectors overlaying that with the dew points greater than 70. You can kind of see that was overlaying the same area. And then putting it all together, you can see the difference between the surface winds pointing to the northwest and the winds aloft pointing to the east. And so you kind of get that cross or shearing, wind shearing effect. And the best way to talk about what that does in the atmosphere is through the illustration of the paddle wheel. And most of you are familiar with this, perhaps. The paddle wheel, if you had a strong flow at the top of the paddle wheel and a weaker flow at the bottom of the paddle wheel, that paddle wheel would tend to rotate. And so that same process actually happens in the atmosphere. So here's an image of some towering cumulus taken by Skip Talbot back in 2010. This was before the battle. South Dakota tornado F4, mile wide. This was some developing cumulus out there. So you can imagine, you can see the wind. Well, don't imagine. You can see the towering cumulus are growing and then kind of getting sheared over. That means they're kind of tilting. They're not going straight up, but they're going over. And you can imagine they're getting hit by pretty strong winds just above the surface. And then beneath that, you may have maybe weaker winds. And if you put the paddle wheel, the giant invisible paddle wheel in between that, you might get a sense of rotation in the horizontal. So that's something to keep in mind. So when you have wind shear, you'll get these basically a tendency for air to spin horizontally. Also, something to mention, baroclinic boundaries equal better shear. And baroclinic, don't worry about that. It just means density difference across a boundary. That typically means better shear. So here's an illustration of that. So you see this a lot, particularly in the May and June timeframe, looking for outflow boundaries as you tend to see a decrease in the overall environmental shear. So you're looking for areas of enhanced shear. Outflow boundaries are terrific for that. So you have relatively cool outflow on the left here and sort of the warm ambient air from the Gulf of Mexico or whatever on the right side. And so the cool outflow will be going down and towards the right, and the warm sector air will be moving over that. And that creates kind of this horizontal circulation situation. So that's another source, kind of a local source of that horizontal rotation that I was talking about. So here's a good example of that. So that opening image that I showed of the Dodge City, Kansas tornado event, May 24th, 2016. This is the outflow boundary that existed in the morning on that. So you can see it stretching from southeast Colorado to northern Oklahoma and kind of curving up towards northeast Kansas. And as time progressed and the sun came out, this was more towards 1 or 2 p.m. You can see that the north side of that boundary. This is something I would really point out, especially for instability. I know we're talking about shear, but you really do want to see that sunshine on the north side of the boundary. That's very important for developing better instability. But here you can see that as time has gone on, that boundary has modified very little. And what that does is you can see that you have relatively backed winds to the north side of that boundary, which is what you would want to see if you wanted more spin in the atmosphere, like I was talking about with the shearing effect. And so you would imagine that there would be pretty strong shear, particularly on the north side of that boundary. And in fact, that's what happened. Storms went up and produced lots of tornadoes, as many of you know. Okay, hodographs. Now this is getting to the fun part. This is my first time going through hodographs, so forgive me if there's any errors here, but I think this is pretty much the gist of it. So hodographs, very important concept in meteorology, particularly with severe weather. Just want to talk about what this is. So if you can imagine, you're just stacking wind vectors on top of the center of this graph as you're going on up in the atmosphere. So for example, if you have a southeast wind at the surface, say in this case about 12 meters per second in this case, so it's pointing from the southeast to the northwest, and then let's say you've got a wind that's at 3 kilometers, so higher up in the atmosphere, that's really strong. This is, an incredible low-level jet. It's coming out of the south, and it's at 35 meters per second, which is completely ridiculous and would never happen. But just for the sake of this illustration, that's where you would plot it from the center, following the direction, so to the north, and then ending where that magnitude of the wind speed ends. And then going on up to 6 kilometers, say a little weaker wind from the southwest to the northeast, perhaps around 20 meters per second, and then 7 kilometer wind, a little stronger, higher up towards that tropopause. So how you would construct your hodograph is you'd actually you see where the arrow tip is, you'd follow that tip, and that would be the trace out of the hodograph. And that's how you create a hodograph. So that line that you see in the hodographs, if you're clicking on Pivotal Weather or whatever you use to find hodographs, that's how that's traced out. And storm relative winds is a very important concept for the hodograph. So storm relative wind, let me explain. So let's just say that's your storm motion. So the storm relative wind would be the vector from your storm motion. So in this case, so if you follow the center here and then move off to the northeast, that may be a storm motion of about 5 or 7 meters per second to the northeast. Well, if you get to the tip of that vector, that's where your storm motion is. And now that you're at the tip of that storm motion vector, now you're going to follow that to the hodograph. That is your storm relative wind. And that goes all the way through the hodograph. And what does that really mean? So the concept of relative motion. So you all experience this every time someone's speeding past you on the highway, or perhaps you are more likely the red car passing everyone else. So let's say you're going 50 miles per hour in a 35, and you've got this slowpoke here going 30. Relatively speaking, compared to you, he's moving in reverse. So he's going 20 miles per hour in reverse. And that's the same thing we're talking about when we're talking about storm relative winds, is that it's about the reference frame, in this case, the red car. Okay, when we're talking about storm relative wind here, so that the actual surface wind was from the southeast right here, but the way the storm experiences it is more backed from the east-southeast. And so let's go to tracing out shear vectors. So we've got all of our wind vectors from the surface on up to 9 kilometers. The shear vector is simply it goes from the head of the lower wind to the head of the upper wind. So in this case, it goes from the surface wind tip to the 3 kilometer wind tip. And then you do the same thing if you wanted to wanted to find out the surface to 6 kilometer wind shear. That would be that right there. And if you wanted to do the surface to 7 kilometer shear, it would be the next one, and so on to 9 kilometers. So that's what we mean by shear vector. And so when you're talking about shear vector, again, We've got, the air pointing in that direction with the upper winds, and then the weaker winds beneath that. You've got that sense of rotation. So what we want to think about is the right-hand rule. And if you've ever been in physics or meteorology, you understand that the right-hand rule means you point in the direction of your vector, and then whatever's to the left is your resultant vector. In this case would be the vorticity vector. So shear vector is pointing in the direction of kind of those upper winds, and then the vorticity vector to the left of that. And bear with me, the reason for this is important. So in this case, you can imagine your little right hand following all those shear vectors on up through the atmosphere. So fingers pointing in the direction of the shear vector, and thumb pointing in the direction of the vorticity vector in all cases. And so if you apply this to your hodograph line, you can imagine that there's all sorts of little vorticity vectors locally. If you take what they say the local derivative at every point, you get all these little vorticity vectors pointing essentially at 90-degree angles to your hodograph line. The reason this is important, that was a big setup, but you put it all together, you got the storm relative wind working with those vorticity vectors. So you see the storm relative winds, same winds that we talked about before, working on through that hodograph. So now we're ready to talk about streamwise vorticity. So in this case, we're again back to that paddle wheel example. We've got that stronger wind at the top of the atmosphere, kind of higher up in the atmosphere, and then the lower atmosphere, weaker winds. You got this rotating sense there with that vorticity vector in the orange. Okay, so you've got the upper wind or the shear vector pointing in that direction, and then the vorticity vector going to the north. In this case, the storm relative wind, if it's pointing in the direction of that vorticity vector, that is what we call streamwise vorticity. So what that means is that what that storm is experiencing from a sense of the environment is, I'm getting a text here. Let's see what we got. 10 minutes remaining. Okay, so I'll get moving here. So what you're seeing there is that the storm is essentially absorbing more vorticity because the storm relative wind is parallel to that vorticity vector. Now, if it were orthogonal or at a 90-degree angle, that storm relative wind would not be taking any of that vorticity into the thunderstorm. So essentially, it would not be taking advantage of the environmental vorticity. So putting that all together, you can see that in this particular case, you see that storm relative wind is oriented almost parallel to that vorticity vector. And so what that means is that right there at that surface wind, you've got some very strong streamwise vorticity. Now, or actually in this case, probably would be a 1 kilometer wind, be strong streamwise vorticity. Now, further up, you can see that they come almost a 90-degree angle here, and that's actually crosswise vorticity. So that's something to keep in mind. And the reason that the streamwise vorticity matters in the hodograph generation is this critical angle. And let me zoom in for you to see what that looks like. So in this case, you can see that the storm relative wind and the vorticity vector are nearly aligned. And the angle between the hodograph and that vorticity vector is this right here. And you can see that that is almost 90 degrees. And so that's what you're really looking for when you're thinking about the critical angle that has been associated within science with the higher incidence of tornadoes. Now that can be off to 70 degrees or 60 degrees or what have you and still have tornadoes. But if you see a 90-degree critical angle, that tends to be pretty helpful for your hodograph. And then storm relative velocity. So that is just simply the area that's swept out between your storm relative winds and your hodograph line. And so some ways you might increase that. Let's say that you're, okay, let me actually take a step back. The most important thing is, and here is the low level helicity. So when you're thinking about helicity, we're more thinking about that lower part of the atmosphere, say below 3 kilometers. In particular, 0 to 1 kilometer helicity is really important to look at. And this would be mapping out the surface to 3 kilometer helicity. And if you wanted to increase that, maybe you would drag it out to the bottom and to the right. So slower storm motion and off to the east, you'd get more helicity. Or if you wanted to increase it further, perhaps you'd back the surface winds. So those winds going from, southeasterly at the surface, from the center to the tip of this vector here, you might say more of an easterly wind. That increases the storm relativity. So sometimes slowing storm motion, turning to the right, and the backing of surface winds can be important in increasing wind shear. A deep layer shear is really an important piece here. It's the total amount of shear from the surface to, say, the mid-level, 6 kilometers. I would say it's just a necessary condition for supercells, generally speaking. And the rule of thumb that I have is greater than 35 knots for supercells is what you want to see for deep layer shear. Here's a case where you have as much of it as you want. This was the outbreak on, it looks like April 14th in 2012. I believe there was some tornadoes kind of sweeping up from Woodward all the way up into the Wichita area and on up into the Salina area. There was a pretty actually picturesque tornado closer to I-70 there. But you can see here 50, 60, 70 knots, plenty of shear for supercells and other storm organizations. So that's what you'd like to see if you wanted to see a supercell. Obviously, you had some long trackers there that day. And then kind of looking at another case, not much shear here, 30 knots. I would say this almost falls below my rule of thumb. But in fact, you did see a tornado near Orienta, and that was because of an outflow boundary. So just because the deep layer shear doesn't quite look sufficient for supercells doesn't mean you can't get, a supercell in tornadoes. It just depends on local conditions. Boundaries really help for that. So low level shear, as I alluded, storm relative velocity in the 0 to 1 kilometer layer is the most important, I would say, or even 500 meters in some circles. They think that may be more important. It's used for tornado potential as opposed to supercells. I would say looking for, in general, 100 meters squared per second squared or more. And then for those violent type tornadoes, if you see above 300 meters squared per second squared, that's really impressive low level shear. On the date with these tornadoes in the plains, you saw a massive low level shear across the board over 300. So definitely brought up to mind the potential for strong and even violent tornadoes. That date out there, June 13, 2007, near Orienta, Oklahoma. I don't actually have the shear map for that, but there was very little on the SPC mesoanalysis. So we've gone through it. I'm going to breeze through the lift part of this since we're running out of time, but you can talk about different types of synoptic scale ascent, large scale ascent. That's really important for developing sort of the key surface features like low pressure, et cetera, that give rise to the organization in the surface pattern. But I'm going to skip right over to mesoscale ascent, given the time constraint. So let me know if you'd like to know more about this after the presentation. So mesoscale ascent, really some things that you really want to look for in terms of lift. Boundary intersections, really important. In this case, you have a dry line on May 31st, 2013, the date of the El Reno tornado, sort of a dry line bulge, and it was intersecting with the stalled front. This is where a lot of that air kind of converged together, and air that's converging together, it can't go into the ground, so it has to go somewhere. So it went up and storms formed. Another key factor in producing lift is dry line circulation. This is a bit of gobbledygook from paper I read recently, but basically you're looking at some cases you have this dual dry line structure. You have a western dry line and an eastern dry line, and in between you'll see these cloud streets oriented along the shear vector. Typically, they call them horizontal convective rolls. And basically, where these intersect with that eastern dry line on kind of this southwest and northeast intersection is where you'll actually see some enhanced convergence. So if you're looking for storm development, that eastern dry line, particularly where it intersects with these cloud streets, is preferred. You can see that here with kind of the look of this dry line. You can see some cloud streets here. Looks like probably more south-southwest to north-northeast orientation of the shear vector here, but when you put it all together, you have moisture, instability, wind shear, and lift. And let's put it all together. You've got that graphic that I've been showing all along. You got that wind shear with the turning in the horizontal direction. You superimpose an updraft in the middle of that, and what you get is that a bending of that vorticity. So that was pointing in the horizontal direction explicitly. Now it's part of it is pointing upward. and you've actually got counter-rotating vortices, as it turns out. So the northern one is spinning in a clockwise direction, and then the southern one is counterclockwise. And through processes in the atmosphere, the southern one ends up being the favored circulation, and the northern one goes away. And ultimately, you end up with a rainy downdraft. And that looks like something you've probably seen before, the supercell thunderstorm. And so that's how you put a supercell together. Those are the ingredients that it requires to get there. So with that, I'll go ahead and finish sharing.
Okay, I want to have everybody give Gabe another round of applause.
Okay, so everybody please bear with me. This is the first time I've done something like this. My name's James Menzies. Obviously, I'm one of the hosts of this convention, and I've been chasing for 20 years, and also done a lot of broadcasting work with camera gear, and I studied broadcasting and photography as well. What I want to do today is I'm going to make this a little bit shorter, this talk, because we are running behind. What I'm going to do is just go over a couple of cameras that I think are some of the best to use when out in the field storm chasing, mainly also because of the lack of noise when it gets dark when you're chasing, also in-body stabilization, so you get steady video when you're chasing, anything from that. And then also what I'm going to do is later on, after I've gone over some of these cameras, I'm going to hand it off to the next speaker, and then when everything's finished later, I'm going to actually come back on at the end after all the speakers to go over a bit more. If anybody wants to stay behind and learn a bit, that's fine, and I'll do it. But I also want to go over noise cancellation software in post-editing in Premiere Pro. And also, there's one, sorry, I've gone blank. This is the first time I've done this. Yeah, so that's basically what I want to do. It's not like an amazing talk, because I didn't have a lot of warning on to get this put together, because I needed to fill a space. So, but anyway, let me get started. And first I'm going to start with the Sony AX53. This is a great video camera for storm chasing. A good thing about it is it's 4K. It has HDMI output on it. But the best thing about this camera is the in-body stabilization system that it has. It actually has what we call a floating lens. So when you're moving the camera around different directions, the iris and the lens kind of move or stay in the same general spot as where you're pointing the camera, rather than moving with the camera. They're good cameras. I've shot a lot of video on these, especially air shows. And they have just great color definition. The sensors on them are really nice and crisp. There's multiple formats to choose from when shooting video, so you can keep the file sizes small as well. And they work off a 2/3 Sony sensor. Now this camera, it's not brilliant for when you start getting dark in lower light situations when chasing, but when it has a noise, what I call a noise boosting system on there, where it basically increases the amount of light that comes into the camera. It actually it's got like an amplifier in it, which goes all the way up to, I think it's 28 dBz of amplification. But obviously the higher up you go on that number, the more white noise and pixel noise you're going to get in the camera. But that to me is still a great camera. It's pretty small, very handy. You can jump in and out the car with it. It's nice. I like it. It's got a smart shoe plate on the top there, on that section just behind the microphone, where you can actually add like lights, an auxiliary microphone, and all sorts of little attachments and everything. The only thing about this camera though is when you use the HDMI output on it, if you try and record and HDMI out at the same time, it will actually shut off the HDMI output when you hit the record button. This was something that Sony, I think, messed up on. But a lot of times you don't usually stream and record off the same camera. Well, at least I don't. Oh, what's going on with the microphone? We good? Okay. Yeah, so yeah, other than that, unless you're actually going to be streaming and recording on this camera at the same time, it's not good for that, because the HDMI turns off when you hit the record button. It's got a single memory card slot on it, and oh boy, yeah, it's I like this camera. I've got one at home. I've used it for air shows as well, for filming planes. It gets really nice steady footage, especially for shooting planes and fast moving objects. I'll go on to the big brother of this camera. It's the AX700, and the only real difference on this camera and the AX53, it's still got the floating lens system on there, which gives you the in-body stabilization. This camera is more of a manual camera, and I'm zooming in to show you here. Here you've got actual full iris control, ISO, and shutter speed. To me, this camera actually, I think, for low light situations is better. It's obviously more expensive, but for low light situations, I think it's a better camera. And bigger sensor, that's another good thing about it. So the low light on it is much better. I've used mine up to, it goes up to I think 28 dBz on the gain, and I think up to about 24 dBz is where you start seeing some serious noise actually appearing in your videos. But for nighttime chasing, this camera does really well at picking up low light. It's really crystal clear video, and the fact that it has manual controls along the bottom there, so you can actually pull it out of auto mode and do your own iris, ISO, and shutter speed like a DSLR camera is really, really handy. So, but this is a good camera. I also recommend. The stabilization on it is not quite as good as the AX53, but this is a camera that would definitely be good for, you know, shooting tripod outside, and the AX53 you can maybe do handheld or vice versa, one on a car dashboard. The AX53 is good for a dash camera because it's small and compact. You can fit it on your dashboard. And the good thing about it is that when you're driving down the road, you know, you can see the front of your car moving up and down, but the camera is like still pointing in the same direction. So that in-body stabilization system works really well when it comes to driving down dirt roads and bumpy roads. It pulls great video through the front window. Okay, next we have the Canon R5. Great DSLR camera. It's one of Canon's new range, mirrorless. Shoots 8K video, shoots up to, I think it's 20 frames a second bursts. It has very, very, very fast focal points, which is good for when you're chasing. Now, I will say to people, don't drive and take pictures out the window at the same time while you're driving. It's not a good idea. So, but yeah, the good thing about this camera is that it's fairly compact. It's a lot smaller than most DSLRs used to be. Canon have really done a nice job with it. My only criticism on the camera is that the video files are ginormous. So using it for video is definitely a no-no. So if you're thinking about this camera just for video, it's fine, but you're going to need about 5 billion terabytes of computer storage to actually hold the files on this. I think they're something along the lines of 6 gigabytes per minute of video, which is just a ginormous size. I don't know why Canon did that, and they could have made the file sizes smaller, but it was that they keep getting bigger and bigger all the time. I don't know why. But it's a good camera. Like I said, it's got a very, very good range of lenses. I personally tried the camera. It was nice up until it broke on me after the first use. So I wasn't very happy about that. But all my friends are getting them, using them for sport photography, wildlife, storms, lightning, time lapses. The camera overall is one of the best ones. You could only go a step further, which would be the Canon R3, which does 30 frames per second bursts in RAW, which is just, you're at video speed at that point. You might as well just shoot a video. So, and let's just quickly go to my personal favorite, which I'm using now. No, not that one. Oops, that's the wrong one. Let's see, here it is. The Sony Alpha 1. This is Sony's recent flagship camera that rivals the Canon R3. This camera, it's a $6,300 body. It's incredibly expensive, but they have achieved everything the Canon hasn't. The good thing about this camera, it shoots 8K resolution video, and the file sizes are only 200 megabytes a second, as opposed to 2,800 megabytes a second. So I've been doing a lot of shooting with this camera this year. I took it to an air show, 2 air shows actually down in Florida. I don't want to get onto that, but I shot 8K resolution video throughout this whole second day of the air show, and I was pulling DSLR quality still images off of that video and then editing them in Photoshop like I'd just taken a regular photograph, and it blew my mind. That camera is incredible. It's so compact as well. It does get a little bit warm in hot weather. 8K video would be a stretch after 25 minutes because the camera does start overheating. This is one of their only problems they're having with this camera. But as in terms of good low light, it's phenomenal. It has what's called dual ISO, which basically means if you take your regular 400 ISO and bump it up to 800 ISO, 800 is going to be basically double what the 400 is, but it's going to be amplified. So take that 800 and double it again. That gives you 1600 effective ISO at just 800. So you're getting a camera that can actually amplify over and over and over to create really incredible low light video. I actually shot some video with this a few nights ago, and you could actually see the Milky Way haze, and this is coming from Oklahoma City. So, and I was pushing at 32,000 ISO, and it was crystal clear. There was almost no noise in that video. So as a low light camera, this is really good. Downside, it drinks batteries. But if you want a go-to camera, especially in cooler weather, that does incredible video and takes 50 megapixel stills at 30 frames a second in RAW, which is just mind-boggling when you think about it, because cinematic video is at 24 frames a second, which they shoot in Hollywood. And this camera is shooting 30 photographs a second for up to, I think it's 280 images. So you could basically turn that 30 frames a second into like a small video clip, but you know, with raw settings that you can edit later. So they're starting to come a long way. Cameras are getting to the point now where the video quality is so good that you can pull frames from them, from the videos, and it's literally at DSLR photograph quality. And this is something I've been kind of hoping for. And what I'm going to do is end it there because we are running out of time for the next speaker. And then what I'm going to do is come back later on and demonstrate some of the noise cancellation software that you can use in Premiere Pro to pull noise out of your videos if you've shot them in low light. There's a couple of things I want to go over as well, like the difference between rolling shutter effect on a camera and global shutters. So we're going to leave it there just for the minute, and then for anyone who's interested and wants to know more about that can come back after we finish later on with the last speaker. So I am now going to hand it over to the next speaker. It's going to be Randy Denza.
Hopefully this works. Okay, so my topic tonight starts off with having a fun chase, right? You're all having a really good time chasing a nice storm someplace, you know, and it's going really great. You're high on adrenaline, you know, everything's going really, really good, and then all of a sudden, oops. Hang on. Wow, it skipped a slide. And then that happens, right? And what I want to do is be able to talk to you about a few points on this thing to, you know, on basically when you get into a disaster, how to operate, you know, what some things to do, some things not to do, and some things to look out for. And I'll go back to who I am. And I started spotting in the Dallas area in about 1990, 1991. I was on a little volunteer fire department. So my first days of actually chasing, which was local chasing, I was doing on a fire truck going code 3. So that was a lot of fun. Throughout the 90s, I did that. It seems like I got to see a lot of tornadoes and a lot of severe storms. I always, when we got to the county line and got to the edge of our territory, I always wanted to be able to keep going, but I couldn't because we had to stay in district. So finally, in the early 2000s, I started storm chasing. So for anybody that's been around for a long time, I was lucky enough to chase with Vern Carlson and a bunch of other guys back in the day and had a blast. I'm not nearly as active as I was back then because I've got life responsibilities that have kept taking me away from stuff, but that's about to change, and I'll explain that in a second. My day job, obviously I'm wearing this uniform for a reason, is I'm Battalion 2B shift with the Austin Fire Department. So I run an entire northwest side of Austin on the B shift. I'm also a vice president of our union. I'm very involved in wildfire response in the state of Texas. I take crews out all the time, not just in Texas, but California and all over. I'm also work for the International Association of Firefighters. I'm in a wildfire task force and a lead instructor for both the United States and Canada. On the weather side today, I'm still on AMS committees for fire weather, and anybody who's been through the online Skywarn program, I helped build the ACES program. So we'll talk a little bit about that here in a second. So we talked about that. You're having a good chase, and then all of a sudden you show up in this. My question is, how many of you all in here have been chasing someplace, having a good time, and showed up on something bad? I figured about that many. For those of you who haven't, the longer you chase, the more likelihood of it happening. And when you do, there's some things that I want to talk to you about on what to do and what not to do. And I want to talk to you about rendering aid, what that means, what it should look like, what it shouldn't look like. How many firefighters, police, and medics do we have in the room? It does not apply to y'all. You do have to do something usually. Depending on your state laws, I don't have a choice. In the state of Texas, I'm a state commissioned firefighter. If I come up on an accident, I don't have a choice. I got to stop and help, okay? But as far as Good Samaritan laws, I'm gonna cover one here in a minute. You don't have to stop and help, and I need you to understand that. Why is it people stop and help? Because we're good, right? Good people stop and help. I mean, we don't want to see other people suffering. If there's something we can do to help, then we kind of want to help. I encourage you to do so, but there's some parameters you need to follow when you do stop to help. We'll talk about those. So out of the people who raised their hands and said they've stopped at a car accident, how many of you have ever stopped to help out a destroyed home? Okay, how about a destroyed town or city? How many of you all have been in a major, major disaster? And that's exactly kind of the percentages I thought, right? It's no fun, huh? All of a sudden you got that adrenaline rush going, man, you're having a great time, you're cruising along, everything's going great, and next thing you know, that tornado's going through a city, right? Or you got a major hailstorm going through someplace. That changes everything. And that creates a lot of stress on you, on the people that just happen to, and the responders. We're gonna talk a little bit more about that as I go on. Are chasers more prone to experience this stuff? Absolutely, right? It's part of it, right? I don't think anybody in this room is gonna say, yeah, I just can't wait to go to the next disaster, right? I just don't believe that. I think what we wanna see is tornadoes are out in the middle of nowhere. So, Good Samaritans, what's a Good Samaritan? It's somebody who stops and helps out. I want to put this picture up because the guy, let me see if you can see him. Well, now it's kind of cut off. Okay, the guy in the yellow shirt in that top picture, his name is Fred McGee. And the picture below, it's kind of not cut off, but you can see in the background, that's the state capitol. I was on my way home from work one day, looked over and saw a police officer carrying an AED, which was a big deal because our cops didn't have AEDs at the time. It was the first AED the city of Austin ever put on a police car. And this cop happened to be at the right place at the right time. And he was running over there with this AED, and I saw it, and I was like, what the heck? So I pulled over and ran over to where he was at, and Fred McGee, the guy in the yellow shirt, was doing chest compressions on the guy in the black tank top. So we sat there, we worked on the guy and everything else. We put that AED on, and it gave us a shockable rhythm. We hit zap, and the guy came back, right? I've never seen, it's really interesting because in my world, in my line of work, we make saves on occasion and stuff like that, but nobody's ever really excited. I've never seen somebody so excited in my life as Fred was after that moment. So if anything, stop to help out. If it ends up really being a good thing, it can be the best thing that ever happened to you in your life, right? If it doesn't work out, like a lot of times, then it doesn't work out. But being a good Samaritan is a good thing. So we're going to talk about how to help. And it starts with step one, which is calling 911. And the reason I know it seems simple, it seems like it would be a no-brainer, but I need you to understand something. Anybody that's in this room, storm chasers, even though you look around, you see other people on the phone calling 911, I really need you to start calling 911. And here's why. You go to a 911 call center in Austin, Texas, I've been in there a bunch of times, phones are ringing like crazy, right? You pull up on something, right? You're a storm chaser, you're kind of an adrenaline junkie. Anybody in here not an adrenaline junkie? You wouldn't be sitting here if you weren't, right? If somebody's not an adrenaline junkie, then whatever. So you should be able to handle stress a little bit better than the average Joe citizen, right? Does anybody disagree? You should be able to handle stress better. So when you listen to those calls that come into the 911 center and you see something like this, you know, or you listen to the calls from that, average Joe who's lived in the house next door will tell you that, oh my God, the whole city's destroyed, right? Is that accurate? It's not. I'm sorry that the picture's cut off, but what I was going to point out was that the glass is intact on the house next door, which has, you know, that's pretty significant, right? I mean, if the glass is still intact, it wasn't a very large spread tornado, obviously. If houses were destroyed here, Tim Marshall will have to explain that to you, but the truth of the matter is if there's only one or two houses on the ground, that's really what you need to report, right? So I would rather, and I encourage you to understand that you're better off calling 911 because you will be able to provide better information than the guy or girl who's really wound up. You're going to see locals on the phone like this, they're probably screaming, oh my God, hurry up and send help, it's terrible. You all will be able to, in a calm manner, be able to say, we have 3 houses on the ground, I have power lines down, you know, and this is at the corner of this street and that street. You're going to give a better, more accurate description to the call, to the 911 center. So I encourage you, if that's all you do, you realize you've just rendered aid. You've started the ball rolling in the right direction. That's the most critical thing for us. So how to be an asset. Good size up is what I was just talking about. You've got to make sure that you relay to them what you actually see, not projections. You can't sit there and say, well, I bet you the whole city's destroyed, right? What you want to, just like when you're reporting a storm, you want to make sure that you say, hey, listen, I have 3 houses on the ground, you know, I have power lines down, they look like they're residential lines, I have walking wounded, you know, blah, blah, blah. You just say exactly what you see. Don't make any projections or whatever else. But that size up begins the process for us when I show up on a fire engine. Back when I was an engine officer or company officer on a ladder truck or an engine, when I pull in, the first thing that I have to do is size up the scene. It looks really weird to the citizens when you pull up to a big disaster and I get out of the truck and me and my guys are actually just looking around. Looks like we're not doing anything. Truth of the matter is we're doing the most important job that needs to be done at that point in time, which is actually getting the ball rolling in the right direction. Because once I get engaged in patient care and I've got a guy laying over here and we start doing that, we're not able to provide that critical information back to dispatch to get the right amount of resources coming. And the right amount of resources means the right amount of resources. It's really kind of an odd thing to understand, but if you said, oh my God, send everything, and we send everything and we don't need everything, that's just as bad as not sending enough, just so you all know. It's really, having too many resources, I saw that at Greensburg, is a disaster. But getting that ball rolling starts with a really good 911 call. Please be the ones who do it. So if you decide to go on beyond just actually calling in and doing the 911 notification, if you decide to move forward, there's a rule that you need to follow. Rule number 1. What is that rule number 1? Don't get hurt, don't become part of the problem, right? It's really easy to do. It's really funny because when I was putting this presentation together, I just typed in Good Samaritan, and you know what most of the stories are about? It's about good people who got killed trying to help other people out, usually at car wrecks. Take a look at this one. I'll whip through it real quick because it's hard to read. The person was killed walking back to their SUV after helping out. Right? There are so many stories, story after story after story of Good Samaritans getting killed. That means that person doesn't get to spend their retirement. That means that person doesn't get to go home to their loved ones. They don't get to see their daughter from high school. That's scary. Or from anything else, right? It's really funny because I'm a good Christian man, and I had a Houston captain not too long ago tell me something. He goes, Randy, I've never seen a happy dead guy. right? So let's just stay alive. Rule number one, don't get killed. Don't become part of the problem. The moment you become part of the problem, you've increased our workload. Now, I'm not going to tell you that we're not going to do everything we can to help you out, because we are. We're not going to be mad at you. But the truth of the matter is try not to become part of the problem. So don't get hurt or killed. Don't become part of the problem, and follow ACEs. How many of you all know about ACEs? Anybody heard about ACEs? Okay, so me and Josh Jans built that. We adapted it from the wildland world of LCES and put it into ACEs, because ACEs was easier to think. We'll talk about it a little bit more here in a second. Couple things I want to talk about on hazards. How many hazards do you see here? There are so many hazards, man. It's amazing when you go into a disaster area. For those who have been in disaster areas, these are very, very dangerous areas. There's so many dangers there. It's literally, you could sit there and write down probably 150 different hazards that you face in these places. And I started writing them down and stuff, and I was going to do it. And the one thing I want to make sure that you all understand, that your best asset for helping an incident commander might be, and that is providing real radar information. I'm telling you right now, I've done that a bunch of times in Kansas, and through the years, I've pulled up to an incident commander someplace or that first aid company and said, hey, there's no storms coming for 15 to 20 minutes or an hour or whatever. Do you think that's valuable information? Yeah, absolutely. That might be that storm chaser thing that we all should start to do, is try really hard to find the incident commander, don't interrupt him or her, wait for the right time and say, I have live weather information for you. I promise you, they're going to say, stay right here, stand beside me. We'll talk about how they act here in a second. Yep, and because one of the most important things we got to worry about, how many have ever been at a tornado someplace, have done damage, and then you still have another tornado coming through? Medicine Lodge, Kansas, years back, I was on a tornado that ripped the Robinson's house apart. That was a long time ago. And we're sitting there, and all of a sudden a tornado came up. We had to take shelter inside the basement of the house that was already torn down, because we had a tornado do the same path. So I want to talk real quick about power lines, and two different hazards, power lines and then people. Power lines, what I want everybody to understand is, please always treat them like they're live. One of the worst fatalities I've been to in my life, of all the fatalities, the worst fatalities I've seen are usually electrocutions. You don't want to be electrocuted. It's not fun, right? I will tell you that the grids are run by a computer, so when a computer recognizes that, hey, we've got a power loss in an area, the computer tries to reset. And I'm speaking in very general terms. This is not, don't quote me on this. I'm just telling you, I've been taught so many different ways about this, but the commonalities that I've been told is that they'll try to reset those power lines 3 times, right? Anywhere from 15-second intervals, depending on where you're at, to 15-minute intervals. So a dead power line can re-energize. But there's something even worse that's going on today, and that's that backfeed. And I'm seeing this every time we go to house fires these days. What happens now, there's such an increase. Everybody has home generators now, right? Especially after last year in Texas with the ice storm, that generator sales went up like 900%, and all my neighbors have them now. We all have home generators. Do you think that a licensed electrician installed those generators? Those generators, Uncle Joe or Nancy's brother, who used to be an electrician back in the 70s and stuff, and they don't put that backfeed protection in. Solar panels are the same way. We had a close call about 3 months ago at a house fire where the outside division claimed the power was cut, and a solar panel power backfed through a line and zapped somebody, one of our firefighters on the incident. Enough so they got put in an ambulance. So they'll backfeed. So with all these home generators, if they don't have the right cutoff system in place, it will backfeed. So you could be sitting there and all you are walking around in power lines, everything's cool, and all of a sudden in 1 second it's not cool. Because usually when there's power lines in the ground, you think it's wet too. So it conducts a lot of, that water carries. So it's please, always, 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 no matter what you see, pretend like the power lines is live. I don't care if you have 10 people standing there jibber jabbering. I don't go near them. Greensburg or wherever else I've been in the disasters, I'll tell you a funny story about cops. Because we had 2 cops join up with some firefighters to do search and rescue in Greensburg. And I told my buddy, I kept doing this to him, and he's like, "What are you doing, man?" I said, "Let these cops walk ahead of us in the water right there, the power lines. Let them walk in first. If they get electrocuted, we're going the other way." I swear that's true. So another thing that needs to be relayed to 911 is whether they're intermediate transmission lines, residential. I know that this is kind of hard, but there's 3 different size power lines generally. Okay, there's the big transmission lines and the big giant power poles, you know, that kids like to climb. There's intermediates, which is what these are, then there's residential. If you can tell them what size lines it is, it's a big help. And the reason is because whatever you're telling them, if you're near a big city someplace, the firefighter are getting their information through a computer. They type it all in. I got it sitting in front of me, and so I'm reading it as we show up, right? It's giving me all my size up information I can get even before I get there. And in there it will say, hey, there's intermediate lines on the ground. As soon as I see that, I press my button and I say, dispatch from engine 23, will you do me a favor, notify electric? I want to go ahead and shut the grid down at the corner of Cameron and Runberg Road, please. I mean, we have the authority to do that, shut grids down in those areas. But we need to know, because I'm not going to do that for a residential line. But if you said I have a transmission line down, I'm going to go ahead and shut the grid down in that area. Okay, this is the other big hazard I want to talk to you about, because this is going to lead into my final discussion today. So you see that guy? Pretty mad, isn't he? That's what people look like in disasters. You know why? Because that guy is going to tell you that his family, and I know this from experience, he's going to tell you that his family is stuck in the basement, and he wants you to come help him get him out. You're walking around in there, right, because you've decided to go in and help. This is one of the biggest hazards I've faced, and probably one of the biggest learning experiences I've ever had through my disasters. I'm not surprised by it anymore. I know that, and that's why I'm trying to relay this on to you. This guy right now is facing a big crisis because his wife and kids are trapped in a basement. But the truth of the matter is that the people who are trapped in their basements and okay, that's one thing. The people who are trapped in their basements and are not okay, who are actually injured, are the ones we need to go help first. So on these disasters, when you show up, there's not enough people. I wish there was. I've showed up on a lot of stuff in Austin. I've been in big fatality fires and big, ice storms, everything else. I wish we always had enough people, but we don't. So we have to do this really painful thing, which is called triage. And so we show up, we size up the incident. The next step is for me to start triaging what we're going to do, right? Put an action plan in place. When I put my action plan in place, it might be not paying attention to the people who are just trapped, because I have to get to people who are injured. And so with that being said, you all need to realize that when you go into one of these disaster areas, that he is rightfully angry. He's really wound up because of incident stress. Incident stress affects everybody. It's going to affect you, it affects the first responders, and it affects the people who just went through it, right? We're going to talk more about that here in a sec. But I'm just going to tell you that he is probably rightfully so angry. He's just been through a really terrible thing, and he demands that you just walking down the street, for God's sakes, the last thing you want to do is, while this guy's doing this, you don't want to take pictures of his house, do you? Right? Be very mindful and respectful of that. It seems like, I know we have laws that protect us, with the media and everything else for doing that, but there's a right time and a right place for that. The right time is not while this guy's out there mad at you or mad at everybody because he wants somebody to come and help, because you're an able body, man. I need you to come and help me move some freaking lumber out of the way so we can get him out, right? And the stress is real. Stress is real on both sides. You're going to be under stress too. So risk-benefit analysis, I just want to briefly go over this. Risk-benefit analysis. When we pull up someplace, I'm trained, and I've been trained for years, to identify hazards and then perform a risk-benefit analysis. I do it in about 6 seconds, just based on my experiences. I've had a lot of experiences since I started driving a fire engine in 1979. That dates me, doesn't it? Risk-benefit analysis, RBA. So what I want you to understand is this. If you decide to go help, remember, is the risk worth it for the reward? So in other words, risk versus reward. Is this really worth it? And what I'm trying to tell you is this. You see that disaster area, there's good reason for you not to do anything. Just get on the phone and call and not go in there. I'm not going to tell you that's not okay. It's okay if you're not trained to do it or whatever else. Sometimes That's what you got to do, because you got to understand that if you don't do an RBA, you don't do a risk benefit, you might go in there and get yourself hurt or injured. So you pull up to a car with there we go, thanks. So you pull up to a car that's been on fire for a while and somebody's in there and you want to reach in there and grab somebody. This is kind of painful to talk about, but the survivability profile is pretty low, right? Or is it worth the risk to try to get to something that's not viable anymore, a person that's not viable? It's a tough decision to make. This is the stuff that firefighters do pretty regular basis, right? We do this risk-benefit analysis. Is it worthwhile to put firefighters into flood water when we know that they get swept away all the time and we lose firefighters' lives every year? The swift water, is it worth it, or do we wait till the water goes down? Right? Sometimes it's just wait for a while and things will get better, and sometimes they don't. So make sure that you understand that when you go in someplace, you really got to think about what risk you're taking, and is it going to benefit? Is it going to help people out? You have to make that decision. That's up to y'all. So let's say you've done your risk benefit and it's time to lend a hand. How can you do that? So we talked about it already. Make sure you maintain your ACEs. Awareness is situational awareness. Maintain your situational awareness. The problem is, and there's lots of books out there on situational awareness. I've been through I don't know how much training on situational awareness. Truth of the matter is that it's really hard to maintain situational awareness unless you're standing there doing nothing but looking around. And it's really interesting because the next time you see a disaster and you see fire companies, you'll notice that there's always usually somebody who's standing there doing nothing but looking around. We have to stand there, and the company officer is maintaining safety for their crew just by sitting there and scanning everything and watching out for new hazards. Communications, if you're going to walk into a disaster scene, I highly, 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 I can't say this enough, call your wife, brother, mother, sister, whoever. Call a fellow chaser and let them know, hey, listen, I just pulled up in a really, really bad scene. I'm going to go in and try to help out. And then I will check back in an hour. Let somebody know what you're doing. Because guess what? If you haven't called back in 2 or 3 hours, they need to call somebody and say, hey, my buddy was there and he decided to go help out and I haven't heard back from him. That lets us know that we got to go look for somebody. Escape routes, always maintain 2 whenever possible. Make sure that you identify your escape routes. I never go anywhere where I can't get out of, and it's really a bad thing because I know this guy does it too. When we go to restaurants, just so you all know, the way we're trained, we do weird things. I never have my back to the door, right? I always look for 2 ways out of the restaurant. I guarantee he does too. We just don't even know we do it anymore. We've been doing it for so long. And safety zone. When I say a safety zone, if you're not sure about weather coming, make sure that you can protect yourself from hail and tornadoes. Make sure that you have some place. And a safety zone's only good if you know you can get to it. So if I identify a safety zone, it's 3 blocks away, but yet we got something coming. It's going to mean that I have to get to my safety zone in 15 seconds. I'm not going to be able to make 3 blocks in 15 seconds. So you got to make sure it's close enough to work. So I'm going to go over just real quick the Good Samaritan laws. If you're not a firefighter, or police, or EMS, then you have laws that actually protect you from liability as long as you do a couple things. We're going to talk about those couple things, right? Remember, calling 911 is rendering aid. The laws that are out there to protect Good Samaritans are dependent on the state you're in. I looked at a bunch of different ones. There's some real, I guess, some basic generalities that I want to talk to you about. Number 1, you don't have to help, right? You are not in a position, unless you're already in the first responder community, you don't have to help. We do it because of the goodness of our heart. We got good people in here. You've done it before, and I hope you do it again safely. The underlying part, I need you to pay close attention to that. You have to act rationally, in good faith, and at your level of training. At your level of training, right? So you can't go in there and all of a sudden say, hey, my God, this guy's choking. I'm going to do a tracheotomy on him. I'm going to go ahead and cut his throat to do it or whatever. That's not your level of training, right? You have to operate within your level of training. On this one, it says that, on this one I pulled up, it says that you basically have to have emergency care has to be given you know, and not in a grossly negligent way. In other words, again, you have to do, you know, rational things, and you can't be the one who caused the emergency. So they won't cover you if you crash into somebody and it was your fault, and then you go try to help them out. You still do it, but that's not what this is. It has to be a result of emergency, and you can't be the one who caused the issue. I don't think anybody here can cause a disaster. So, best thing I can tell everybody in this room, and I can't say this enough, is get CPR training. Can't say it enough. Get CPR training. Get CPR training. If you want to take it a step further, get a first aid class. There's a new thing out in Texas called Emergency Medical Responder. I think that's National Registry, so I think that's everywhere. There are classes that are 40 hours out there that might save your family's lives. It might save your family's lives or your friend's life. You just don't know. Once you have this training, it might be amazing who you end up using it on. You have no idea. But it sure would be nice to be able to do something for somebody in your household when they need it, right? You know, I'm going to tell you something when we get to the last slides. There's nothing worse in this world than feeling helpless, right? So you all are in a risk. We've all agreed to this. You're all in a higher risk of coming across disasters or bad emergency scenes. So since you're at a higher risk, I'd highly recommend you get some training. And it's available. You just look on the internet. So the first responders arrive. They're here, thank God. Everything's going to be okay, right? Wrong. So I want you to know that the first responders, when they show up, I talked to you about sizing up and stuff. They got a lot on their plate. I'm going to talk about their stress. This is their community usually. First ones there, this is their community. Might be the worst thing they've ever seen, right? In their own community, they're under stress. I know this for a fact. I've been there, done that. And I deal with good Samaritans and bystanders all the time. And I'll tell you something, 90% of the time they're fantastic. 10% of the time they're kind of a pain in the butt. And there's actually 1% that we have to do something about them. But most of the time they're really, really good, all right? But understand something, when the first responders show up and they get out of their rigs and they're doing that looking around thing and it looks like deer in the headlights, they're actually processing stuff. Don't think they're ignoring you. Just be patient. Stand there and say, hey, I got some information for you. You want some information? They'll usually look at you and say, okay, what do you got, right? But let them kind of process what they're processing. If you run right up to a company engine officer just getting off of a fire engine, off a ladder truck, a rescue truck, whatever, if I'm just getting off and you come up and try to get my face and start talking, that's not the time to do it. I'm going to ask you to stand back. I'm not being rude. It will come across as being rude, but please understand the first responders are not being rude to you. This is a big deal for them. They got a lot on their plate. They got a lot of responsibility ahead of them, right? Just try to relax a little bit, be a little bit patient, and then at the right time, that person's going to look at you. I'm going to tell you that I've had bystanders that I've put in for major awards. I've sought out Good Samaritans that I've put in for some major awards. The tornado that went through Rowlett back in Christmas tornado a couple years ago. There was a guy there that worked with me all night long that I put in for a major award. The city of Rowlett gave him, I don't know, some type of I don't know what it was, what award it was, but I got to go there and watch him get it presented to him because he did such a good job. Just be patient and understand the stress. Okay? And I can talk really loud there. So we already talked about triage. I'll skip that. And just know my whole point of this is I just want everybody to understand that there's stress at all levels. Everybody's under stress, okay? And the good information to pass on, I want you to say, when you pass on their stuff, if you can write it down or whatever else, I'm going to tell you something. I know it. Just say, hey, here's my name and number if you have any other questions. I've wished that 100 times. I've had so many people I wish I could have said thank you to that guy. He probably thought I was a giant you-know-what because I was under stress. I wish I would have had his name and number or her name and number so I could call him back and say, hey, listen, I really appreciate what you did. I'm sorry I wasn't in my right frame of mind, but I have a lot going on. I had a lot going on at that moment. So if you can, I know it sounds crazy, but try to write down your name and number. Just say, hey, if you have any questions, sir, just give me a call. I wish that 100 times. Real quick before we go to the last little section, decon. So if you ever go in and help in one of these disaster areas, you have no idea what could be on you. You could have crystal meth on you, right? You would not believe all the stuff that's in here. There have been a lot of studies done on our firefighting PPE that just one incident, they take our PPE away from us and then they go in and analyze it and stuff just from smoke and everything else. The stuff on there is crazy. So this is something that most people don't know, but one of the first things we do when we leave a disaster scene, especially water rescues anymore, is we decon. We do gross decon at the scene. We'll spray the heck out of everybody, you know, before they take their gear off. Then when they get back to the station, they shower right away. And we use soap and all kinds of these wipes that they have for us now that kind of helps try to get all that other goo off. Because there's in those disaster scenes, remember that just knock toilets down, right? So there's poo and there's kinds of fun stuff out there. So make sure you decon yourself. Don't forget to do that. So this is the last thing I want to talk about before I turn it over to Eddie. So I've already taught you about incident stress and what it does. And I've studied this for years, and I've been a part of studies and everything else on incident stress. And folks, I manage fires every week. You know, I manage big incidents every week. And I just know this for a fact. And it's really funny because it's not until late in your career where I'm talking to other firefighters or buddies like Jeff Petrowski. We just talked about it a little bit ago. Man, you know, all this stuff is cumulative. There's a responder stress. There's stress on those victims that were just part of this disaster, and there's going to be stress on you. When you pull into an incident that you were just high as a kite on from an adrenaline rush, and you pull into a major disaster, it has a profound effect on you, whether you realize it or not. After Greensburg, I was really blessed. And what I was blessed about was that I had some crews that I worked with at the time. I was on Engine 40 in Austin. And after I got back from Greensburg, it took me about 5 days. And Engine 40, Ladder 40 personnel sat me down and said, "Hey, you're not yourself right now. What's up? You need to go get help." And I said, "What? You guys are crazy." And they said, "No, you haven't been yourself since you got back from that thing. You're not the same happy guy that you were before you left." I went and got help for about 6 months, okay? This stuff is tough. These disasters are tough. Me and Jeff were just talking about it. It's tough stuff, and it's cumulative. So if you've been to more than one or two of them, it builds up. You know, this incident stress, post-incident stress is a real deal. So what I want you to all know is that there is a phone number, and I don't care if you write the phone number down now, but what I would ask of you is understand that you can get on Google and say, "Hey, I was just at a disaster, I need help, disaster helpline." I called this number and told them I was doing this presentation, and they were like, "Oh my God, that's great." You know, and we started talking about it. I said, "What resources?" "Well, this is through FEMA, and they will put you in touch with people, even non-first." But you don't have to know the phone number. Just know that you can look at Google and say disaster helpline. So I encourage you, after you go to the next disaster, if you pull up, even if it's a couple houses or whatever, if you start feeling bad, you feel a little bit blue, a little bit on edge, you needed somebody to talk to, you call them, and guess what you're going to talk to? You're going to talk to people who know exactly what you're going through, right? I guarantee it, people working these lines are the same. They're people who have been through it before. Otherwise, they wouldn't be there. So with that, I'm going to turn it over to Eric, and then if you have any questions later on, we'll do it after Eddie. Jeez. Eric Fox isn't here.
Oh, is this one? Sorry. All right, guys, I'm Eddie Aldring. Thanks for coming tonight. Thank you for the board of directors for having Randy and I up here to talk. Randy talked about the safety side of things. I'm going to be kind of talking about the do's and don'ts of the legal side of things when we're out chasing. So I'm Deputy Eddie Aldring. I work for the Cass County Sheriff's Office in Cass County, Missouri. It's the next county south of the Kansas City metro area. So we get a little bit of rural, we get a little bit of urban calls in our county. I used to be a police officer at El Dorado, Kansas, and Derby, Kansas, which are both suburbs of Wichita. Was down there for a while, took a little break, figured out I missed being in law enforcement, went back 2 years ago. Actually, 2 years ago today, I started at Cass County. So, patrol deputy there, was born and raised in Topeka, Kansas. I've lived in Wichita, was in the Air Force for a while. Now I live in Belton, which is in the far northwest corner of Cass County. So, chasing professionally for 14 years, so since 2007. Before that, I was chasing storms right when I could drive. So I'm 39 now, so cops are bad at math, so I can't really do that off the top of my head, but been doing it for a while, so it's a good hobby. The job keeps me busy, so I don't get out as much as I used to. To get this joke out of the way, people ask, this is your joke, Randy. How many donuts have I had today? I have had 0 donuts, but I've had tons of Power Rings. Those are my favorite. Now this next one is pretty self-explanatory. I just got to change the picture. Now for you guys, it's a pig who caught another pig. So I don't know which one's more unhappy, but all right. So here's our overview. Being in law enforcement, I know a lot of people don't like us, and I want to make sure that I'm not here to tell you what to do. I'm here to give you guidance to keep you out of trouble when you're chasing, okay? We'll go over general laws. Due to time, not because we're running short tonight, but just because going through every state that we can chase in, it'll take forever talking about laws. So just tonight, I'm going to talk about Kansas, the best state ever. I know you Texas people are kind of, yeah. Nebraska, Colorado, Oklahoma, and Texas. And then if we have time, we'll go over questions too. So general laws, I mean, we all know we need to stop at stoplights, stop signs. I'm not going to say who this chaser was, but some of us older guys know who that was that ran a stop sign, killed himself, his friend, and then another innocent person in a car. So with speed, keep it within reason. I know if you need to get out of the way of a tornado, do what you need to do. But once you're not actively going, if you're jumping from storm to storm, be smart about it. I mean, obviously, the faster we go, the more dangerous it is. So there is one thing that us law enforcement officers have, and every state has this statute. It's called the basic speed rule. We don't have to catch you or anyone else on our radar to be able to write a speeding ticket. We can know just by looking how fast that you're going, saying, yeah, that guy's definitely way over the speed limit. So that's one thing you really have to watch out for. And I don't write a whole lot of tickets, but if someone deserves it, is being stupid, then we have to do what we do, and a lot of law enforcement officers are that same way. Also, passing on straights. I know a lot of people like to cut it close. We have a famous truck that passed on a curve a few years ago. That's a big no-no. And then passing on hills, you got to watch out for too. So Kansas. The big thing that a lot of chasers do that I've seen, and I'm guilty of it too, driving across farmland to kind of save some time. We all saw it in Twister, driving through cornfields and things of that sort. If you're caught doing that, you can catch a charge for property damage. And depending on the amount, you could get a fine or even be charged a misdemeanor. So with a misdemeanor, you can do jail time. With the criminal charges, you can get that, but you can also get civil charges from the farmer or the landowner who owns that, who could sue you civilly for damages for that. The obeying the lawful order, that comes from law enforcement and fire. Say we have a road shut down because there's damage there, it's too dangerous for people to go past. If you go around that thing, you could be charged with a misdemeanor. And one thing I want to tell you guys, these 3 laws here, they're not only laws in Kansas, they're in pretty much every other state too. But just to make it simple, I put it on this slide. So the subsequent states after this, then they also have same laws like that. Now we all know driving a big hail, you'll break a windshield. That's a big law. It's kind of hard to explain. Law enforcement, they can stop you just because you have a broken out windshield. Now, they should be smart enough to know that there's storms in the area and that you couldn't help yourself. But that can give them a reason to stop you and go further. Nebraska, so who was down in Mangum, Oklahoma for the tornado? Gerard, I knew you, Beth. A bunch of guys. There was that one intersection there where traffic was backed up forever because everyone and their best friend was on this storm. I saw a lot of people that were wanting to go straight or turn left that went into the other driving lane and did that, or they went on the shoulder and did that too. So Nebraska, that is a state statute that you cannot do that. And like I said about Kansas, that law is in every other state too. So with reckless driving, it really depends on the law enforcement officer, what he does. There's certain elements of the crime that he has to check off to charge someone with that. But with your first offense, that's a class 3 misdemeanor, so that's a ticket, could be jail time if you want. Second offense, class 2. Third offense is a class 1, which class 1 misdemeanor is right below felony. So if you have subsequent reckless driving charges on your thing, you could go straight to a third, even if it's your first time getting it that day. So, what was it? Jordan, what was the big outbreak that was in Wichita in 2012, April 14th? Yeah. Up in Solomon, Kansas, which is west of Wichita, in between, or not west of Wichita, west of Topeka and east of Salina, kind of right in the middle. There's a bunch of people that were stopping on bridges. And those of us who have been around for a while knew about the county emergency manager who was bad-mouthing chasers because of that, when it was actually a lot of his local chasers that were doing that. So because bridges don't have wide enough shoulders for us to park on, and even though they give us good vantage points for storms, don't do it because your vehicle will be in the driving lane and then it can cause a crash. Now I got the same problem as you. All right, Colorado. I know a lot of chasers have been outfitting their cars with sirens and PA systems. Every state that I've talked about tonight and will talk about, and even the ones that aren't included in the slideshow, all have laws about no sirens or no PA systems. So I know a bunch of people put these PA systems on their cars to notify people of impending tornado or whatever. That's a big no-no too. I believe almost every state that I looked at, it was a misdemeanor. So that's definitely something you don't want. Now, Colorado being recreational marijuana, we got to talk about that. You can get driving under an influence when you're high on marijuana, just as if you were drunk on alcohol. So you really got to watch for that. Colorado has a no open container law, just like if you had an open beer can or liquor. So it can't have any broken seals. The contents have to all be there, can be partially missing. And then there's no evidence of consumption inside the vehicle. And then if you were to buy some there in Colorado and bring it over into Kansas or any other states that border Colorado, you can get federal charges on transporting, and then also get state charges from that too. So it could really hem you up, make your bad day. Definitely something that you guys don't need, so just be smart about it. Oklahoma, this is another law that has in every state. Crossing railroad barriers or ones that have the flashing lights with no barriers. If those are down or the lights are going, do not go across. Because I've worked plenty of train versus car accidents in my line of work where they aren't too pretty, and they're there to protect you guys and to protect others, and that poor train operator that has to deal with killing someone when he couldn't slow down in time. Now with radar jammers and detectors, I know a lot of people have them. Every state has laws against them, I believe. I think there's a few outliers that don't. But just watch out for those. That's another thing that can give probable cause to a law enforcement officer to pull you over. We all know people in the chasing community like light bars and flashing lights. Every state has a law saying that you can't do that. So as long as you're moving, driving down the road, you can't have those things on. But once you're stopped, it's okay to turn them on, just as if you had your hazard lights on your car. And what was that at the bottom? Oh, yeah. So emergency vehicles, you can read it here. It's pretty long. Storm chasing vehicles do not fall underneath any of that. So just to protect you guys, keep you guys out of trouble, make sure you guys keep those in check when you're going down the road. Now, Texas, my second favorite state. One thing I like about Texas, they have a lot of good cell phone usage laws. So no one under 18 can operate a motor vehicle, MV, while on a cell phone. So no texting, cell phone calling, look at radar, radar scope or Pickle 3. Now, I don't know what the fascination is with it. People outfit their cars and trucks with horns that sound like trains. Every state has a law against that, especially I don't think you can get one that's under 300 decibels. So it scared the living heck out of people. Crap, I fat fingered it. Yeah. It is fun to scare people, but it can be dangerous. And then no red or blue flashing lights. You can get impersonating a law enforcement officer deal, which is a felony. So that's bad news. One thing to help out Randy, and it applies to law enforcement vehicles too, do not follow them into a disaster scene. That's another charge that you guys can get. Now, I know that we can make some good money with pictures and video of tornadoes going through storms, but that can make your day pretty bad after that. No driving over fire hoses, things of that sort, because you can cut one and then it totally kills their firefighting operations. John, do we have time for questions? No? Okay. All right, guys, I want to thank you guys a bunch. I know we might be scary sometimes, but if you guys see me out here, come say hi. If you have any questions, be glad to help you out. So thank you.
Yeah, so the question would be, how come you're not getting tornado warnings in tornado warning areas, but you're not getting the notification of the warning over your cell phone?
Maybe it's more geared for Tim Marshall because he's more of an expert.
Apparently it is for Tim Marshall.
No, I just survey damage. What does that have to do with a cell phone other than I'd use a cell phone to take pictures of damage? I'm not one of those cell phone kind of guys, you know. I just
I'll take a stab at it.
yeah.
It's very complex, but on the cell phone technology with the EAS alerts, it's going to depend on how good your coverage is there, when did the alert get issued. Sometimes I have seen out in the field that when you have a lot of warnings, you get a little bit of a backup sometimes to getting that alert. But there's a number of things that will cause you not to get the alert, right? And it could be hundreds of different things, literally. But yeah, it does occasionally happen.
This is for Mr. Thompson. Given the forecast for the December 10th event, the days prior and then that day, what led to the outlook being just a moderate risk compared to a high risk right before the event took off?
Well, I figured this question was coming. I was hoping I'd get at least 2 or 3 deep into it before. Okay, this is just, look, I've been at SPC since 1994, so that's a long time that I've been doing convective outlooks. Just being honest with everyone here, I did not seriously consider high risk. I did the 1630Z Outlook update, so I'd inherited an enhanced risk that had 10% significant tornado area. In looking at it about mid-morning, we decided, hey, maybe there's a corridor with a little bit higher threat, but I never seriously considered a double upgrade. That's very rare to jump 2 categories in an update, especially when it's prior to any hint of the storms forming. Now, if your question was referring to later in the event, I can't speak to that as much because I wasn't in the office after 4 o'clock. So when I left, there were no thunderstorms. I mean, there might have been a couple of lightning flashes southwest of Little Rock, but if your question is related to, is that what you're getting at, is like, why was a high risk not introduced, say, at 1Z in the evening update? Well, you know, those sort of things probably depends on the experience of the forecaster and how much the forecast staff is able to talk. The problem with a day like that is that most of the other areas started getting active in Missouri and Illinois prior to the big ramp up in that tornadic storm, which was right at 1Z. So there was no history of tornadoes with that storm as of, you know, because the Outlook update isn't decided literally at 8 or 7 p.m. on the dot. There are, you know, a couple hours of thought goes into it. So by, you know, 6 to 6:30, if you haven't already decided that you're going to upgrade, chances are you're not. You can't just do that on a whim. Like, oh, it just crossed my mind. I'll go high risk and then just click, send it. And then, no, you get in a lot of trouble if you do stuff like that. So I think that, simply put, there wasn't enough evidence by 6:30 to 6:45 p.m. to convince the forecasters that they needed to. I think they thought moderate risk was still a reasonable assessment, and me personally, I never seriously considered high risk in the earlier update. I'm just happy that I went to moderate. You know, I could have left it at enhanced pretty easily. So hopefully that answers your question.
I was there. I'm from Murray, and my mom is in Murray with, like, she's in the last stages of Alzheimer's. And so when that tornado hit, I had actually, as a Murray State alumni, I went to the basketball game versus Memphis that night. And I just wondered, because I'm more of a photographer that likes to photograph storms than a meteorologist, what was what kicked that storm into such high gear? Because I was looking at those forecasts in the days leading up to that, and I'm like, this is probably going to be a little bit bad, but I definitely wasn't expecting it to go that crazy like it did. So what was the meteorology, to a layperson like me, that really kind of sparked the explosion?
I was hoping I could weasel out of this one, but it's nice to see everybody looking at us. Well, okay, it's a good question. You know, what got that, why that storm, why did it ramp up when it did? I think another way to phrase that question is, why did it take it 4 hours to produce a single tornado? The storm formed was probably somewhere between around 3 o'clock or so. It was right around the time that I issued the tornado watch. I think I can't see the images, but if someone can tell me when the watch shows up on there, you could see the outline of it for the counties. Is it? Okay, there it is. So the watch, you see just those towering cumulus clouds in the southwest corner of it. There's no lightning at that point. And this is at like 3 p.m. in the afternoon. So the tornado started about 7 p.m. So I guess that's my question, is not what made that storm itself go, but why did it take 4 hours? Can anyone think of a day that it's 4 hours from storm initiation to the first tornado and it ends up being a huge tornado day? I can almost think of no events that correspond to this one. You know, probably in terms of the storm environment, it looked like a lot of events. I can show you dozens and dozens of days that look pretty similar. I think the real question is just, again, why did we manage to get this one single uninterrupted storm in an area where that doesn't happen very often, any time of year? But, you know, never mind that it's in December. But there's an interesting combination of events that has to occur, and I'm just going to say up front that we don't know how to forecast that. There's no HRRR model run that shows explicitly that. There's nothing that says you're going to get 250 miles of tornado out of one storm. There just was, you have to read way between the lines to get something like that. So it just proves there's a lot we don't know. I mean, I think that, and it's why when I talk to people about the forecasting, there's a reason that we do probabilities. because there's uncertainty in every forecast. If you are honest with yourself as a chaser, how many times has someone turned around, it's like you were going the wrong way and then you figured out something, you got a warning, or someone called you and you turned around, or you did something different. Later you pat yourself on the back, you have great video, great pictures and all this other stuff, but you were an hour before were driving the wrong way. I'm just saying, as a forecaster, I can't do that at SPC. If I'm driving the wrong way, everybody in the United States sees it. So I can't just stop the bus, and this is like turning the Titanic around. Sometimes I just crash into stuff, and there's nothing I can do about it. So that's the way I'd say, is there's more than just why that one storm at that time. It's like why that storm, period.
One thing, the environment was obviously prime. The fact that it was an isolated storm also helped. But how many of us have seen prime environments where one storm is a prolific tornado producer and the one right next to it doesn't do anything? So there's something else out there we still don't know. We can't expect these guys to pick out what storm mode and what storm is going to do it and what storm's not. I have a question for Jeff. Jeff, where did you start that day? How did you chase it? What did you look at? I'm going to ask a lot of questions. and what did you see?
Thanks, Tim. That's a great question. Let me back up for a second on Rich's watch at 4 o'clock. I was just about passing Little Rock at that time. Left Tulsa about noon. Got a late start. Been really busy at work. So I looked at the ensemble models. Looked at the HUR. Looked at the RAP. I looked at the all the cams, WARF and the ARF and the V3, and a pattern about 36 hours before the outbreak started, where we had these real long helicity tracks, really far apart, maybe even 150, 200 miles apart, from Kentucky all the way up to St. Louis, all the way, back way south in northern Mississippi. So as we got closer to the event, those lines started coming closer together on the ensemble models. If you go to the SPC page, look at the HURF, and you look at the ensembles, and you see where they're all kind of, getting closer together. So looking at that, and then as I was passing Little Rock, watching the Tower and Q form in southwest Little Rock, your 4 o'clock discussion was really good because you said there's a 700 wave coming out. It's very pronounced in northeast Texas. It's coming northeast. So I think one of the things that caught my attention is that none of the models handled the storm developing southwest of Little Rock. None of the models, even the 18 or 21Z HUR didn't have it. So that was a red alarm to me in a big way. I've got a storm already up southwest of Little Rock. It's not quite in the moist environment. It's going to be farther east. It's a little bit less uncapped. You get east of Little Rock into the low-level jet. It's stronger. As we get towards 0Z, the low-level jet's going to ramp up dramatically, right? And we're getting away from the cap and ML layer. So the models are picking up that as it gets near Jonesboro, just east of Jonesboro, it's probably the lid's going to come off and it's going to go crazy. So figuring out my travel time and getting over there, as I passed Little Rock, the storm looked interesting back southwest, but I said, it seems to be moving 55, 60 miles an hour. I'm not going to wait. I'm going to go ahead and go up to Jonesboro area. They went east over by Memphis, and just west of Memphis, there's little bitty supercells going, little bite, 20,000 footers. And I looked at them, and they were little bitty barber poles. I mean, real tiny, like 2 miles across. You can see wall clouds from them. I'm like, uh-oh. When you start seeing things that are out of the ordinary, that should be a big-time red flag to you that something's about to happen, right? As this wave's coming, and these little cells going up are already trying to rotate. I'm like, that's interesting. It was about 5:45, 6 o'clock. It's almost dark. I was just west of Memphis, so I decided to go north on 55. And then all of a sudden, the storm came out of Little Rock because it got northeast there. It got its act together quick. Here comes the hook. Here comes the velocities. Low-level jets ramping up. Everything's coming to play. And I'm like, hey, I'm going to cut up to Jonesboro. Well, I cut up to Jonesboro. And it started rotating. And then a lot of things happened southwest. It started tornadoing, right? Didn't see the first couple of tornadoes. And I made a mistake. I went southwest of Jonesboro, about 15 miles. And when I was sitting there on the boundary, I noticed that couldn't see the tornado, but I knew it was back southwest of me. And my winds went from northeast at about 35 to 40. And I'm like, well, the shear is phenomenal in this thing. It's moving into the shear. And then all of a sudden, my winds come around to northwest. And at that time, I launched the radar, and all of a sudden, it was moving northeast. It goes boom, boom. It started turning right. I'm like, uh-oh, I'm too far northwest. Here comes the rain. I go back to Jonesboro, go back east, go on the southeast side of Jonesboro. I could tell the RFD was really intense, and it was getting more intense. So I went southeast of Jonesboro, and all of a sudden I got in that hard RFD winds out of the west-northwest, and it was real dry. I literally saw the wall cloud in front of me vaporize, just disappear, because the RFD was so intense. Well, I was like, man, I better keep going east. So I went east. Next thing I know, I see a tornado in front of me about 2 miles, a big stovepipe. But what I didn't know, there's a tornado behind me, which I never saw, but another chaser south of me about 3 miles, filming 2 tornadoes on the ground at the same time, east of Jonesboro. So called the first one in, live tweeted that out. And then as the storm got past, as that tornado passed east of Jonesboro there, it made its way back southwest. Think about the first town it hit southwest or northeast of Jonesboro. Moffett. What was the town? Yeah. So I was pulling up there on the southwest side of town, and I could tell bad stuff was happening on radar. It was just intense couplet. And then the next thing I saw was just a wall of debris in front of me, about a half mile. Policeman was in front of me. He was blocking the road. And the next thing I saw was this tornado just take out the northwest side of Moffett heading northeast. And what stunned me, there's 2 things. Normally in the wintertime, you don't think, with 70 dew points, you don't think how you're going to see this tornado, right? So it's kind of a little bit elevated storm. You could see the tornado from 20, 30 miles away. It was, you could really see it. It was really well, right? And especially in that time of the year, December in northeast Arkansas is not what you would think you would see. So as it left Moffett, the road curved on the north side of Moffett. As I came out of Moffett, I looked to my left, and to my shock and amazement, the thing had just exploded in width. It was really wide, but well over half a mile, going on 3/4 mile wide. And I could see this big, huge V, black cloud, and it was just tearing up everything as it's pulling northeast, getting ready to hit the next town. It hit some transmission line wires, and it illuminates it pretty well. So anyway, I ended up stopping at the next town that got hit, which is pretty bad. There was a fatality there, but didn't see that. That was at the local store. And I came up on a scene that was really bizarre to me. There's a high-pressure gas leak, talking about Randy Denters, talking about all kinds of things you're going to run into. There's a very high-pressure gas leak. I mean, it was probably a 10-inch main, probably 200 PSI. I mean, you could hear it from literally like 4 miles away. It was that high of a pressure gas leak. So that was going on. And there was this white across the road. It looked like it snowed, but it was like 4 foot deep. And I'm like, what is that? I didn't want to go up there and check it out, right? But the road was blocked, so I couldn't get out of town. And coming later next day and do naming survey, it was actually cotton bales that went across the road and had the road blocked. But a lot of hazards. And then I finally got east of town, and I saw it leaving that area. I could still see the tornado heading toward I-55. Like 15 minutes later, you could still see it. And it was rocketing northeast. And then ended up pursuing it later after the fact, up 55. But I got too far behind it and left me. So I waited for the second storm to catch me, right back southwest coming up. But anyway, that was a short little clip right there. But things really ramped up at 0Z. The cork came off, and it went to town. That was the long version, sorry.
4 questions. Yeah.
There we go. Okay, so question for all 3 of y'all. Generalized to also this, but also other long track tornadoes in the path. I have a question. I noticed day before the flow was a little bit more orthogonal, critical angle right around 60 degrees, right? So I was wondering, at maybe a more orthogonal flow, is it a little bit more conducive for longer track, like more sustainable for longer track, given better backing from the surface?
I guess I'll take that one first. If I understand what you're saying, I mean, if you're talking about the flow being something about the shape of the hodograph, the change in the winds with height, that being favorable. I mean, look, in my experience, a lot of the long track tornadoes, I mean, the really long track open warm sector stuff, especially east of the meat of the plains, like east of the classic chase area, a lot of times they're longer. They're not as curved a hodograph, but it's a lot longer hodograph. And, that's just seems to be the characteristic. The flows may be a little bit more westerly than you would tend to get away with in the plains. Usually it's more capped. It's a warmer, drier profile if you do that in the plains. But over toward the Mississippi Valley, that's not necessarily a problem. So, they can get low-level moisture with a south-southwest surface wind, and you can have more westerly flow aloft. I think the key in a case like this one, in many of them, is you need enough of a source for ascent to get a couple of storms, but you don't want any more than that. So what you're doing is you're walking this really fine line between absolutely nothing happens in the warm sector, and I get a couple of long-lived storms that don't interfere with each other, or there's just one that goes on for many hours. So that seems to be the real trick. And I wish I knew how to forecast how many storms and how close together they have to form to keep from interacting with one another. if I knew that, we wouldn't be having this conference, because basically I'd just be telling her, oh, well, here's exactly what's going to happen 3 days in advance. There wouldn't be any mystery to storm chasing. We would just tell you, here, there's no probabilities. Here's a fact. This is what will happen. So we're nowhere close to that, and I think that's kind of what makes forecasting fun, but also kind of scary at the same time. So to me, that event and any other one similar to it, it comes down to details that usually involve the initiation of 1 or 2 thunderstorms. And when you're talking a multi-state area, you're talking about some very small changes make a huge difference in the outcome. And stuff like that, we can go back all the way to the May 3rd, 99 tornado outbreak locally that was incredibly subtle where the storm started. And people would say, well, how could you possibly have no idea that there's going to be a multi-billion-dollar tornado? I'd say it's a lot easier than you think.
Another thing, we've all seen, all of us, all the chasers out here, we've all seen cases where you have a lead storm go up, and maybe the winds aren't quite back like we want. Maybe they're 180, 190. But that first storm will put out such a nice outflow boundary, as long as it doesn't get really cold. All of a sudden, sometimes I've found myself on the first storm, and then I look at the back storm ingesting the outflow boundary, right? And all of a sudden, that back storm turns into a barber pole, and it starts tornadoing. You're like, wait a minute, that wasn't supposed to happen. The models didn't forecast that, right? But sometimes you have to peel backwards and go back to the one behind there, and it actually is tornadoing with the first one. I've seen it both ways, right? We all have. So a lot of times we just don't know that stuff until almost it's occurring.
Yeah, it's a storm interaction, as you were talking about. I mean, how many times that we got out there and we're on the first tower, but that goes up, produces a nice storm, but it does not produce a tornado. Maybe something we hear later on, that a couple of storms merged and that ends up producing a tornado. And I've seen it go the other way. I've seen storms merge and then it just collapses. So there's no rule out there, obviously. We just kind of have to depend on our luck. To be out there at a storm, I call it base time. Get as much base time as you can. And that is really then up to luck and whether that storm's going to do it or not.
You had a question.
Oh.
Stand up.
Jeremy? Okay, my daughter and I here were in Mayfield shortly after the tornado to help out. And I want to compliment you guys. First off, we talked to some people in Mayfield that were very grateful for the early warnings they got. And I just want you guys to share your thoughts on that. And I have one second question there too. On the forums and stuff, there's been a lot of talk about EF4, EF5. What's your thoughts on that? Because it's like the damage was there. I don't know that there'd be that much difference in a wind speed of 190 and 200 anyway. And what sort of things did help you guys determine that?
Mr. Marshall.
4 or 5. Let's just put it this way. It was a violent tornado. So what difference does it make if it's 4 or 5? Well, I'll tell you, in order to be a 5, it's got to be up there with the big boys. All right? The Bridge Creek, which scoured vegetation. Gerald, Texas, which not only scoured vegetation, but it removed road pavement. All right. Mayfield was not that. Mayfield destroyed houses, for sure. But if you look at how they were constructed, a lot of these were older homes, pier and beam foundations, not anchored. All right. Just fodder for tornadoes. And it doesn't take a 200-mile-an-hour wind to blow away those houses. It doesn't even take a 150-mile-an-hour wind to blow away those houses. Those houses were going to go much, much earlier. So in order to rate something a 5, you need to have something that could withstand that, have a resistance to that. None of the buildings that I looked at could do that. So churches, a lot of them were built in the 1800s, double width masonry, big, steep roofs. They collapsed just like a house of cards. The debris was not blown away. It was just collapsed. So metal buildings, the candle factory, it's designed to the same design as your house. 90 mile per hour, 3-second gust. Those big metal buildings cannot tolerate 150 mile an hour wind, let alone a 200 mile an hour wind. So we just don't have the markers. And that was the big problem in the El Reno tornado, was everything went away at EF3. So could it be EF4, EF5? Of course. but there's no markers for us damage-wise for EF4, EF5. Radar picked up EF5 in a grassland, okay? Then unless we have a building there, what are we rating? We're rating tornadoes, we're rating damage. Well, right now the scale rates damage. So if there's no damage, who knows? It could be EF4, EF5. But Mayfield just didn't meet the bar. Part of that, I think, is because of the fast movement. It was moving at almost 60 miles an hour, wasn't it? It was really fast. So you calculate that out, it's only over a house for seconds versus Gerald, Texas, which was moving at 9 miles an hour, about the same speed. And if you calculate that out, it's over the house for 3 minutes. Does duration make a difference on EF ratings? Yes, it does. But we don't have a way of really trying to quantify it. But Gerald was a very slow, violent tornado that ended up scouring the ground. Houses were basically polished slabs. I mean, it went down, took the commode, took the bathtub. Those would not have been safe places to be in. It just took everything. It just left slabs.
I'll make one comment or a couple of comments. Most people don't know this. I built houses in Tulsa for about a little under 20 years. I built close to 500 homes, including commercial buildings. And I can honestly tell you the damage I saw in this Mayfield event, all the way from Arkansas, all the way, way east. There's no other nice way to say this. The construction on virtually every building I saw was poor to very poor. And as Tim's alluded to, it was horrible construction. I'm telling you from the builder's perspective, it was horrible construction. I call it the brother-in-law construction. Hey, Joe, come over and help me build this deal in the back of my house. I'm going to add a slab. I'm going to throw this together. And Tim's right. I can tell you I spent, I don't know how many hours and days over looking for stuff on my own. And I looked for the really bad stuff. I looked at the radar where the most intense signatures were, where we had the highest debris. I searched high and low. I talked to more people. The most intense stuff I found was east there, where I found 3 cars were picked up. I forwarded Tim in the weather service, and one of them was on 100 yards, another couple hundred yards, and the third one was like 1,800 feet. But even that area, the construction was not up to par. I mean, you really had a stretch, in my opinion, to even get higher than an F3 to F4 range. It was tough. It just didn't qualify. Didn't even come close, in my opinion. It was. I'm just telling you, if you go to look at the damage, house after house, there's no bolts, there's no straps on anything. A lot of the buildings in Mayfield didn't even have standard brick ties. This is standard minimum stuff, guys. Brick ties on buildings, but as Tim said, all those buildings were in the 1800s, early 1900s. Brick ties didn't come out until probably in the 60s, roughly in the 70s. So a lot of those buildings didn't have the basic stuff that you would expect today, right? So as Tim said, you get a storm moving that fast, it's not going to take much to tear it down, and that's basically what they found through their investigation and the research, and I can back it up. It was not up to par. I mean, a lot of the stuff was not up to par that you'd expect in F4 and F5. It didn't meet the criteria. So I agree 100% with his assessment, the weather service assessment. They were dead on. I mean, it was absolutely perfect. Yep, on their assessment.
And if I could add to this, basically, I don't have the damage survey experience that Tim does, and I haven't been probably in as many damage paths as Jeff, and I certainly haven't built hundreds of homes. Built like 2 and over like 30 years. But the whole point here is that these guys don't have agendas. I think people start taking this stuff personally. I don't know when and how we do this. We all do it as weather enthusiasts, where you take a particular event or a forecast personally. Tim's not going out there thinking, evil genius, like I'm going to purposely rate this EF4 to make everybody mad. Because I know it's a 5, but I'm just going to, on purpose, I'm going to call it a 4 and see how much trouble I can stir up. He's not doing that. He's given his best professional opinion, and it is what it is. As he said, it was a violent tornado. That should be plenty.
Well, first of all, I don't determine the rating. The National Weather Service determines the rating. Now, I happen to be in Mayfield. They found out about it, and they said, we'd like you to go look at a couple damage points. But I was just one of other teams that were out there. These other teams was unanimous. None of the other teams that were out there thought it was 5. I think if one of the teams decided it was 5, it may have been a 5. But there were other people. Brian Smith, National Weather Service out of Omaha, was out there. He looked at several points. You know, another team was out there, Mayfield, Dawson Springs. They couldn't find any 5 points there. So it's a team effort. It's not me. I don't rate the tornado. That information goes back to the National Weather Service, and then they come out with a rating.
So for anyone that didn't, if you can't hear the question, it's basically to getting at how do we handle as meteorologists differences amongst the model guidance. Models are constantly changing, especially the convection allowing models, stuff like the HRRR, the NAM-NEST, which, you know, there's any number of these model variants out there. And, you know, I guess the short answer to the question is there is no unique way to do that. I think that the best answer I can come up with personally is that I was fortunate to get into professional meteorology 20 years before we had access to this stuff, so that I can at least have a method in place to make a forecast that doesn't involve any of that detailed model output. And, you know, because I had to make forecasts at SBC before the HRRR existed. I know it sounds amazing, but, you know, we used to have to actually look at upper air charts, and, you know, there wasn't a pretty picture painted for you. You had to come up with all that in your head. And so that it helps to be able to have experience doing that, so that I can independently assess a forecast. And then the way I try to do this most days, not every single day, but most days, is that I use the CAM forecasts. Does this look like something I would expect to see in this scenario? And if I see something that's drastically different, like, wow, I didn't expect to see a squall line, or I didn't think there would be storms there, okay, I'll look at it in more detail. But you know, the problem is, and Jeff had mentioned the SPC, the high-res ensemble forecast, the HREF, that we display on our webpage, which is really just a ensemble of opportunity. It's essentially models that are all different in their characteristics, and we lump them together, and it actually outperforms all professionally designed ensembles, which is kind of funny. It's just by accident. The point is, it shows it hopefully gives you a range of the uncertainty in the forecast. Like, one model core has huge updraft helicity tracks and what look like supercells. Another model has no storms. Another one has a blob or a line. It gives you at least a sense of the range of possibilities. So that's more how I would use it, and not worrying about any one. Now, the problem is when you get competing scenarios that are completely different outcomes. I mean, and just because they all show something similar does not, I can find examples where that doesn't mean that that was the outcome. That just means we all went off the cliff together with a bad forecast. So if I were to say anything in here is to people that the HRRR is very enticing. It updates every hour. It puts out a radar-like picture, and I'm convinced you cannot get that out of your head when you see it. We're used to looking at radar, and when you see something that looks like a lima bean-shaped supercell, that's stuck. You're stuck with that image in your head all day. And just remember, these forecasts are nowhere close to perfect. Look at them in extreme detail, and you'll find out. Don't just say, oh, yeah, I remember seeing some storms, and therefore it was right. No, be pretty harsh on these. Or better yet, next time you chase, drive exactly where one of these tracks is, but you can't go more than 10 miles either side of that, and see what happens. So I guess the point in this rambling is that you have to have a strategy to give you at least a first guess answer that does not include that guidance, because if you don't, you are completely at the mercy of it. Now, if you don't care about meteorology, you know, I get that, but I can't get away with that as a professional meteorologist. It'd be pretty dumb for me to say I don't like meteorology, but I'm paid to get the forecast as close to right as I can, but I know that that includes more than just, I load up the HRRR, I can do that in 20 seconds. Oh, high risk, click, send, done. No explanation needed, but that's not really, there's a lot more to it than that.
Yeah, to me, it's model schmodel. I just look at where all the red dots go on RadarScope.
Well, no, great question. If everyone couldn't hear that, it was basically what goes into the forecast process. How do we make the decision between a moderate and a high risk? And what are there specific thresholds that we're looking at? We look at one variable, like the CAPE goes up this much or the shear increases by this amount, that we do it. I mean, the short answer is no. So that's the art of forecasting that I think people forget, that you can't, this isn't like you're making brownies. Add 1 cup of this, 2 cups of that, a teaspoon of this, mix it this way, put it in the oven for exactly this long at this temperature, and it comes out the same time every time. A forecast is more like, well, there might be some flour in it. Maybe you'll use the oven. I don't even know if you mix the stuff together. It'd be something more akin to that, and the more you do it, the more you understand what we're trying to do is figure out where is the wiggle room in the forecast. And like on December 10th, since that's what inspired this part of the gathering, you know, when I came in, we had an enhanced risk. It was the forecast. So that's the tier 3 out of 5, and it's in the middle. Never mind the arguments over what the words mean, but it was the number 3 on a scale to 5. How do I decide to upgrade that? I think really with me, it was just like, I think I've got a corridor where the balance of evidence suggests that I might get a warm sector storm or two that could be fairly long track. The environment favors significant tornadoes. Now, I have no idea if it's going to be EF5 or EF3. I just don't know. And then we do talk to each other. So there's I would say collaborative effort is the best way to describe it, but you guys all know there is a name at the bottom of the SPC forecast. We're one of the few places left in the world that still do that. So if my name's on it, you can bet I'm gonna pay some attention to it, because I know there could be a conference a month later and they're talking about this one forecast, and then I can't hide if my name is on there. So obviously I'm gonna lean on my own experience as much as I can, but like in the case of that, there was discussion with 2 or 3 other meteorologists at SPC that regularly do convective outlooks. I talked with not so much the local forecast offices, I did about the watch type. There was a lot of discussion with the local forecast offices. So these forecasts aren't done in a vacuum. It's not just me by myself because my name's on it saying just, oh, well, I'm gonna do this and I don't have to answer to anyone. The whole weather enterprise, people are very aware of these categories and probabilities, and when you change them, you better have a good reason. And if you change the wrong way, you are definitely gonna hear about it, and you're not gonna help anyone by going the wrong way. So we try to make it a consensus if we can of experienced meteorologists. In my experience, that works better than any one person doing it by themselves, but there are days where the consensus is even wrong, and no one of us sees it. And no one's asked about the watch for that day. I'm surprised nobody's asked, why wasn't it a PDS tornado watch? We had 2 discussions regarding that. I brought up one in operations, we talked about it. We thought this is right on the edge. We just don't know. And this is before there's any storm. So I can't point to radar, oh, well, this storm, this is why I'm gonna do it. So we're issuing early because people want lead time. But the earlier you issue, the less you know about how it's going to turn out. So you have to think back to what it looked like at 3 o'clock, not what it looked like at 9 p.m. The decision was 6 hours old by 9 p.m. And and I talk to local forecasters when we do a conference call. I don't know if people know this, that when SPC initiates a watch, we start the process, but there were 5 local forecast offices in that first watch. I talked to every one of them. They have a say in the process. Could be, let's add these counties, let's shrink it or whatever. And also should it be a tornado watch? Should it be a severe thunderstorm watch? Should it be PDS? Those kind of things get discussed, and we try to go with as much as I can with a consensus that's based on actual evidence. Not just, I want this with no explanation, but when people state their case and it makes sense, we sort of go with that. And on the 10th, it was like, I don't think we're quite up to the PDS threshold. And it's not, if we did it again the next day, it's possible it would have been PDS. It's just, again, there's an art to this that it's fuzzy is the best way to describe it. There's no just, oh, if this dew point was 1 degree higher, I would have done this. It's if I had known, if I was, clairvoyant or omniscient, yeah, then I would have done it. But other than that, and I don't think that's going to happen, I seem to know less each year that goes by, so I don't think I'm going to be omniscient anytime soon. So it's a collaborative process, and there's clearly more than one person involved. And plus, we respect the previous outlooks, because it's one thing as a chaser to say, oh, well, who cares what the previous one did? You do that and go into work with them. For 20 straight years, you're working with the same people. And then just tell them, yeah, your forecast was crap yesterday. And you know what? If you did it all, I don't care tomorrow either. The workplace doesn't go very well when you're not respectful toward the other people who combined probably know more than I do anyway. So it's an interesting process, but I don't think there's any one unique way to answer any of these questions. Basically, give me the scenario, sit in and listen, see how it goes, and it'll probably be different next time. But very good question, though.
Yeah. I think another thing we all got to think about too, Rich, when you guys is forecast out a couple days ahead of time, is talk about climatology. Let's talk, I mean, when you guys had that enhanced risk, I don't know about you guys, it's middle of December. We're talking enhanced risk, long track damage, tornadoes. I don't need it to go to moderate. I don't need it to go to high. I don't need a PDS. I know bad stuff's going to happen. I didn't drive 7 hours from Tulsa to go almost to Tennessee because I needed a PDS. I knew what was going to happen, right? There's going to be bad stuff happen. Look at climatology. It told us something was probably going to happen. If they went moderate or high, I didn't care, right? I mean, we really don't need to beat up the SPC because they did one thing or another. You got to look at climatology, the region, what part is happening in the past, these kind of setups, and look at that. I think that has a lot to weigh in whether you chase or don't chase and what the outcome's going to be. Nighttime tornadoes, I don't care what time of the year they are, they're dangerous. End of story, right? They're just dangerous. Come on, they're bad, right? Doesn't matter if it's F1 or an F4 or F5. Bad stuff's going to happen. If an F1 hits your trailer at 70 miles an hour, bad stuff's going to happen, right? So that's all we need to remember. Yeah, it's great forecast, by the way. Yep.
Thank you.
I'm going to do it on the microphone too. So I have a quick question for you, Rich. In real time, in a situation like this, other than like mesoscale discussions and watches, what are some other processes that go behind the scenes when y'all are currently tracking the system like this?
Okay, the question is, what is SPC doing behind the scenes, aside from the obvious stuff, mesoscale discussions and watches that we're sending out? There's obviously a lot of discussion amongst the forecasters to the extent that we can. Now, if you keep in mind an evening like that, I was lucky. I worked the day shift. I issued the first tornado watch, and then I go home. And the evening shift came in, and they issued, I think it was 8 or 9 more watches. Well, that takes a long time. There's a lot of back and forth. You can't really issue a watch faster than about 15 or 20 minutes, and that's if you know what you want to do. And then you're trying to think, okay, hours ahead and how this plays off of that, and people, what cities am I including, what counties, what states, you don't want to be too soon, you don't want to be late. You're juggling a lot of stuff, and so it can get to be tricky to keep up with situational awareness because you have a lot of products that you have to do, and sometimes you'd be surprised at how little you get to look at the weather. It's like, I got to make this decision, I got to make this one, then I realize, what am I making a decision based on what? I've hardly looked at anything because I've been on the phone, I've been talking to my coworkers. Those kind of things come up, so there's a lot of banter back and forth between the SPC, and then within the Weather Service system, that's mostly who we deal with. We don't deal with like the media or emergency managers directly. Mostly that's the local forecast offices, but we will be in touch with the forecast offices like over the phone or chat, various chat rooms that we have, and there's plans to do more of that. We're basically bouncing ideas off them. They're asking us questions. Hey, what about this? Have you thought about this thing? But they get into warning mode, and it gets to be hard for them to keep up, because they just want to make sure they're not late on tornado warnings for a dangerous storm. And, so there's a lot of challenges keeping up with situational awareness, but mostly I think it's just sharing of ideas, bouncing stuff off each other. And it'll be 2, 3, 4 forecasters at a time. Because SPC only has like 4 or 5 people on shift. That's the most we ever have. So the short-term weather is usually just 2 or 3 people handling the whole country. And these events, people talk like they're bad. You should try June. When there's like 6 slight risk areas and they're completely different scenarios, all of them, and 3 or 4 are going at the same time. That's when it's bad. Because, it's like you have to basically know everything all at once, everywhere. And that's not easy.
As someone that was there in that area in the days leading up to that event, I told several people that it was going to be bad, and I kept getting the same message back to me of, well, that's what they always say. And I got that attitude a lot. And then when the event actually happened, it was, of course, oh, this never happens here. And so I wondered, for someone like me who's, you know, a kind of amateur chaser, how could I best tell the people around me, this is not the same old, same old. This is something that is very different. Like, when what was kind of the social messaging problems that y'all saw with that storm?
Well, I assume I'll take this. That's like, nobody seems to want to jump in. From the SPC perspective, you know, we do some of the messaging, but most of the interactions with the people in the local areas comes from the local office, because they're the ones that know the people. I may know what the weather, I have an idea what the weather's going to do, but I can't, you know, I don't know somebody's grandma in Western Kentucky. That's the stuff I don't know. I don't know the local details, where people are, what they're sensitive to. I may or may not remember all the past weather events, which plays a role in how sensitive they are to a coming forecast. I mean, you know, so in situations like that, all I can say is what SPC strives to do. We are never, ever going to be the first one on the internet that says, oh, it's going to be big. It could be somebody in this room, I don't know, maybe it's all of you, or some fraction. They're always going to beat us to the punch, because we have to be credible when we say these things. If we just jump out and it's like, wow, that looks great at day 9 or day 10. On the Euro, it's totally different on the GFS, whatever. We can say all that stuff, but we will quickly lose credibility, because we have to do it every single day. And we broadcast it to the country, and basically the rest of the world's at least looking at these things out of curiosity. So we strive to, we're going to be a little teeny bit slow to react compared to, some people are going to say, you guys are always behind. It's because if we just, what do you want us to do? Day 8 high risk? And we would do it one time, we'd look like idiots, they would quit paying attention to our products, and then we'd be in worse scenario than, you know, when they say, well, they say it's going to happen all the time. SPC does not try to do that. We don't say, oh, we say this all the time. It's like, really? We put moderate risks out all the time? I don't think we rarely put them out. And so that's kind of our approach, is that we wanted to make sure that when we have to resort to the big guns, that people take it serious. Their first guess isn't like, wow, they're always wrong. It's like, well, no, it's like, wow, they don't do this that often. That's the way we try to approach it.
Hey guys, quick question, kind of along that same lines. So for quite some time now, there's been, it seems like, a desensitization of the public in response to legitimate watches and warnings ahead of an event. So pretty much the same line, we've got a lot of people out there that are incorrectly calling themselves meteorologists. They don't really have any true education, or they make a Facebook page and call themselves a weather authority or something like that. You guys are the authority, but the general public doesn't understand that, and so they start following these Facebook pages, and maybe they don't watch you guys or the local media, they watch these other Facebook pages. Are there any efforts going on or monitoring of these situations by the National Weather Service, or anything we can do on our end to start curbing this, because it seems to be a continued issue from local media and such going forward?
I've been talking a lot. I don't want to, and I've got it the whole next hour, so any comments?
Yeah. This is a social science problem, as more and more pieces of information that are out there. I personally don't get my tornado warnings off Facebook. Hopefully none of you do either. Cell phone's a good thing to have. In my area, we have an alert system. If we're under a tornado warning, my cell phone actually goes out. Same for Amber Alerts, that sort of thing. It's a good thing to have, because some people don't watch television, especially the news. And you know, with the Doppler radar that's on there with the TV stations, they give some pretty good warning. You see the polygon, you see where it's going. I mean, if you're in the polygon, you don't wait for the car to drop in the front yard before you seek shelter, right? Hopefully not. But everybody I talked to, Mayfield, Dawson Springs, knew that there was a tornado on the way. And maybe not directly, maybe so-and-so called them and let them know that, hey, you know, it's bad to the southwest, watch out. You know, my feeling about the whole thing is, if there's lightning in the west and it's a warm muggy wind, like 70 degrees in December, and you're in Kentucky, storms are approaching, pay attention. There has to be a certain amount of self-responsibility. If you don't want to pay attention, it's your own choice. Nobody from the SPC or the Weather Service is going to come up to you and slap you in the face and say, there's a tornado coming. Do something.
Okay, we're going to make this the last question now.
Hey, thank you guys for what y'all do, and I appreciate it and everything. So I got a question as far as the Mayfield tornado. I noticed on the correlation coefficient, just kind of measuring it out and stuff, it was showing the debris signature being, about 3.5 miles wide. I was curious, how wide was it at its widest point? Is there a better way to get a measurement on radar on how wide a tornado would be? And also I noticed a debris spike signature on there, and I was curious whether this was the first time that radar has ever caught a debris spike. I know typically it's a hail spike, but in that case it was a debris spike. So I was curious whether this is the first time we've actually captured that on radar or not.
Yeah, I was watching it play by play myself as it was approaching Mayfield. On the radar scope is what I was using. You could see the correlation coefficient. Keep in mind that the correlation coefficient is very sensitive to range. It's a range dependent. So it has to be fairly close to the radar in order to see that correlation coefficient. You can see a lot of other things a little further away. You can see velocity couplets further away. You can see reflectivity hooks further away. But so the size of it, of course, depends on the number of scatters that's going through the debris that's going through it. And when debris gets lofted, sometimes you'll see correlation coefficient stretch out in more of a linear fashion because it's being lofted out. So as, of course, your distance from the radar increases, you're looking at higher and higher elevations. So the correlation coefficient may change or weaken, but it really doesn't weaken. It's just getting further away from the radar. Jeff, since you're with the Barron system, you can probably talk about correlation coefficient.
Yeah, I think Tim's dead on. The Mayfield tornado, after it picked up the large amount of debris and it was lofted up over 30,000 off the top of my head. The radar beam, the coefficient in the radar beam, also you get a bending factor with the debris as well as hail. The big hail, it'll bend the radar beam. It bounces back, and when it reflects back, and the radar antenna listens to it, it says, "Hey, there's something really big there." So probably the debris. I haven't looked at the investigation, but the debris had definitely a second trip echo from the debris field being so large, right? So we'll have to let the scientists research that from the lab at Norman, and the scientists tell us what that second trip echo was, that big spike down radial of the debris bowl. But I'm sure it's going to have something with the debris and the intensity of the debris being lofted up. But yeah, the coefficient, you've got to be really, really careful. Gosh, I could talk for 12 hours about this subject. You've got to be really careful. What time of the year is it? Is there trees? Do you have leaves on there? Do you not? If you're out in the woods and you have a tornado on the ground, you may have a real subtle coefficient. You may not have the really big. When it hits a city, like at Mayfield, it got really intense really quick as it hit the plant and hit the big structures there. But if you're in a rural area, it's going to be a little bit more subtle. So you got to be, a lot of it has to do with the time of the year it is and what part of the United States is that, right? Is it in a wooded area? Is it going through a mobile home area where you get sheet metal lofted higher in the atmosphere? So you're going to get the little CCs are going to show up a little bit different depending on how far you're from the radar and what the signature it looks like, right? But there'll be a lot of investigation on Mayfield, I'm sure.
So if you know how that spike works, I mean, the radar doesn't know if it's a hail spike or a debris spike, but typically the pulse of energy is sent out, it hits a target, comes back on the receiver. But what happens is when you get the three-body scattered spike, it goes out, it hits something, it bounces down to the ground, comes back up, hits something, and then comes back. So now you're getting another trip out of that. So it stretches that out. It looks like an echo as a spike, but of course it's false echo. It's just another trip there. So it doesn't matter if it's debris or hail or some biological scatter. If there's enough of it, it'll do that, hit the target, bounce down to the ground, come back up and come back, and you get that false echo trip that shows up as a spike down down radial.
Yeah, that's actually a good observation and I agree with everything these guys have said. I would just add that the width of the correlation coefficient, like the CC minimum, it is probably related to tornado width, but it's not 1-to-1. You'll hear people say, oh, well, the tornadoes too are, in this case, 3 miles across. Same thing with El Reno. The closer you sample to the ground, probably the closer it is to being an accurate assessment. But remember, debris falls out away from the tornado. So it's those large, irregularly shaped things that give you the low correlation coefficient. Because raindrops and things don't look like that. They'll have high correlation coefficient because they're all the same shape and orientation. You get, pieces of a mobile home. Unfortunately, it's fluttering down. Who knows what shape it is. It's all changing orientation. It's basically, think of big things fluttering down. So it probably tells you as much about the debris fallout area and the width of that as it does the tornadoes. Because if you've been around an intense tornado, you'll have little debris and things fluttering down that can be a mile or two away from the tornado. Not just downwind from it, but on the sides as well. You'll have stuff. So I would be careful saying, oh, well, it's a 3 mile wide tornado because this little CC hole is 3 miles across. That just may mean that something is 3 miles across that's related to the tornado.
Right. And a lot of times, Rich, another good example would be the El Reno tornado, right? Or the stuff we've had in May 3rd here in Oklahoma City, when you have you got Josh's team, the Dow trucks out there, and when you look at the Dow per sample, even on the rapid scan, and you look at the CC on those, a lot of times the CC is really tiny because there may be only 2 or 3 miles from the tornado, right? But if you look at the next red, it might be 15, 20, 40 miles away. It's got a pretty good sized little bowl if it's a big debris ball. The closer your sample, the smaller that debris bowl is going to be. So if you got something really small, generally you've got it, the radar is pretty close to that tornado signature. We see that a lot with the debris fields.
Yeah, and then one other thing about that second trip echo, basically the debris spike signature. I think with tornadoes you don't see that very often. I think it has occurred, but you have to be in the right location because unlike large hail, you can have like softball hail at 40, 50,000 feet up. You rarely get tornado debris, especially big stuff, up that high. Right. So you have to be close and you have to be looking at the right angle. You're never going to see that if you're looking northwest. And where are most of the radars compared to the big cities? They're southeast of them, so that they have a clean view into the inflow side of the typical storm. So it has to pass southeast of you, and it's got to be really close. And it's hard to do that. There are not that many big tornadoes, so naturally they don't go just in the perfect spot for a radar to observe them. And that's why you only saw it from Paducah, and you didn't see the same signature from 3 or 4 other radars that sampled it almost the same way.
Yeah, I think we're time's up on that one, but thank you very much, guys. That was awesome. Appreciate it.
All right, looks like we are good to go. I don't know how late we are. What are we on timing? I don't even know where we... 9:45, so I got 15 minutes. So I can do it. It'll be interesting, but no, I'll try not to keep us too late. And the way I'm going to structure this is really it's like 3 or 4 smaller presentations in one. And if we need to, the stuff at the end I can skip if everybody's had enough. And what I'll do is I'll take, if there's questions at the end of each little section, so I'll kind of stop, and if there's questions about that, I'm not going to make anyone sit for 30 minutes to ask a question on something that was that far back. So again, I'm Rich Thompson, a lead forecaster at SPC. I'm in year 22 as a lead forecaster, so some of the younger chasers, well, are y'all surprised I'm still alive? Is that what that is? Sometimes I wonder, and I've been at SPC this is like year 28, so I've been doing this for a long time, but I was a chaser before I was a forecaster at SPC, so this is my, kind of my heart still lies in the storm chasing, and I still try to do it as much as I can. It's not as much as I want to, but I try to keep up with it. So anyway, over all the years, there's been one question that has come up hundreds and hundreds of times, and I really haven't had an answer for it. And it's about the convective outlooks. And people want to say, well, what do you think's going to happen? I get questions all the time about, well, tell me what you really think, as if I'm putting out a public forecast that is fake. And I'm saving the real forecast for you asking me on the side. It's like, but it's like, what do you think? When are the tornadoes going to start? Are they going to be visible? Am I going to take good pictures? And it's like, well, I don't know. Are you going to be in the right place? Do you know how to work your camera? I mean, there's that kind of stuff. So the part I can look at, though, is that how do SPC forecast? What happens when we get supercells that produce tornadoes during daylight? What do the SPC forecasts look like? Because there's some people that say you guys are always wrong, or we have one of the female forecasters. You guys, you gals are always wrong, or you always do this, you always do that, and I'm like, yeah, always. You know, they say that as a parent. Don't ever say that to your kids. It's always and never, because that's never the case. Point is, you may be remembering one forecast where you got mad, you screwed up on a chase, and then you got to blame somebody else. It's my fault because I didn't have a high enough outlook probability or something. So what I want to do is I said, hey, wait a minute. I finally have the data based on other projects we've been doing for several years. And I want to say, what do the SPC outlooks look like? So what I'm going to do is I'm going to go through and verification that is a chaser-specific verification of SPC products. If it happened overnight, don't care. If it was with anything other than a supercell, don't care. This is all purely supercell daylight type storms. So working with some of my coworkers, we've got this huge database of tornadoes where we've looked at the radar for literally tens of thousands of storms over the last 12 years, going back all the way to 2003. This is all published stuff, so we've tried to share it and through the peer review process. And we know what kind of storms produced each tornado. And what we've done is we have filtered the tornadoes. It's on what we call a grid hour event. If you look at anyone remember the old RUC model? Who remembers the old RUC model? It's the RAP now, but the grid spacing that the original RUC model had, that's what we use. So we have a grid, and we say what was the maximum rated tornado in every grid box for every hour, and then we go back and load the 88D data to try to figure out what kind of storm structure was associated with each tornado right before the tornado occurs. So we've done that with, I think our spreadsheet's like 46,000 rows of stuff. There have been dozens of people working on it for about 12 years. But with all that sitting there, it's like, hey, wait a minute. I know what kind of storms there were. I know when and where the tornadoes occurred, and I work at SPC, so it's not that hard to find the outlook. So what I've done is I've tried to look at only tornadic right-moving supercells, only during the daylight. Again, I wasn't ultra precise. I didn't do these goofy local solar time down to the minute stuff. I just used some rough guesses where, you know, like sunset in the middle of the summer, like 1:30 is like 8:30 at night, Central Time. So it's generally you can still see and then 23:30 is like 5:30 in the winter. Depends on where you are, but you can still see in most of Central Time Zone. And I didn't count tornadoes that occurred before 16Z. I know chasers don't seem to be morning people, and I'm not one. So I don't expect people to be up at 7:30 and it's like, wow, did you see that great hose over there, you know, east of Wakini or Kansas or whatever. Nobody's chasing, not nobody, but the majority are not chasing in the morning. So if it's not close to lunchtime, I don't care. Basically, if I would be asleep on a day off, I'm not going to count it. So we're looking at basically late morning through late evening. So again, these are just grid hour events, not tornado counts, but it's the number of times a tornadic storm occurred in those. And I break it down by season. I'm going to break it down by region. And then I look at the outlook probabilities and the outlook immediately before each single event. So anyway, the idea here is it's not really tornadoes specifically, but it's more grid hours, or you could think of it as chase hours is probably more what I'm looking at. All right, here's how I broke the U.S. down. If anyone's offended by the West, I'm sorry. There's just not enough events west of the divide. I know the Central Valley and that stuff. If someone's serious, I'll send my email at the end of this. You can send me a request to look at just say California or something where, you know, there is at least some sample. I can do it, but this took a long time to dig through all this stuff. These are just rough guesses. Hopefully, do you think you understand what the abbreviations are? You know, high plains, HP, not heavy precipitation. And, you know, northern plains, central plains, southern plains. The east is just the E, you know, that kind of stuff. The only one that's tricky might be the Ohio Valley is what I mean by that for OV. So Midwest, Ohio Valley, Southeast. So I looked at these regions, and I'm going to break down the convective outlooks by season and by region. And again, keep in mind these are just daytime tornadic storms. So the things to consider, my regions are not that precise. I was drawing that in PowerPoint with rectangles. That I mostly use state borders. If you looked at it and noticed that, hey, wait a minute, why was Southwest Texas left out? I did not leave out Southwest Texas. If you like to chase by Midland, they were in this. I just couldn't draw rectangles the way I wanted to. So again, I'm lazy. I don't know PowerPoint as well as probably some of you. And so again, these are fuzzy borders, but a pretty good idea. And then there were some times where I counted multiple events in the same region. I'll show you an example of when that would come up. And again, this isn't explicitly tornado count. It's more like tornado chase hours within a few county area is about the size of the area we're looking at. So now I know everyone would want to know. It'd be great if I could tell you something about what SPC false alarms look like. If you can tell me a unique way to know that a forecast was for daytime chase storms in an SPC Outlook without me reading 10,000 discussions in a row, I'm all ears, but I don't know how to do it. So I said false alarms are just something that I can't really address at this point. And so again, here's just some examples of what it would look like. This is an easy one. Each of the tornadoes that are circled were produced by a right-moving supercell and occurred during daylight, and they were in 3 different regions. The one that looks like it's over roughly Maryland, that was the east region. Everything, I just lumped the Atlantic coast together. The one that's over West Virginia counted as Ohio Valley, and then there's one up in North Dakota that would be Northern Plains. So this is just an example of what I did. And I did this for every single day that had a right-moving supercell tornado for 6 years. And the reason I use 6 years is because I wanted to use the forecasters who are currently working at SPC. So this applies to the people who work there now, not somebody who was there 20 years ago. Now, here's an example of one. Some of you may recognize the day, May 17th of 2019. I would guess the majority of chasers were probably in Nebraska if they had a choice, but there was also a nice storm down by Dodge City. The point here is you notice the outlooks are much different. Even though Kansas and Nebraska would both count as the Central Plains, the outlooks are pretty substantially different between those 2 corridors of tornadoes. So I counted this as 2 events. So there's one forecast that's 2% down by Dodge City, and it's 10 sig up for the Nebraska tornadoes. Now you might wonder why don't the Texas tornadoes count? I'm from Texas. Why didn't Texas count? Any guesses? Well, they do, but why would I not count it? And not just because my boxes were biased against that one little corner. That would be one guess. That'll be relevant on the next example. What's another one? But that's not why this one. What am I focusing? Nocturnal. It occurred at night. These were supercells, but it was way after dark. So now here's one when you mentioned QLCS, like the squall line tornadoes. Ton of tornadoes, the Easter outbreak from 2020. I only used the Bassfield, Mississippi tornadic storm because that was the only corridor with daytime tornadic supercells. All the rest of that stuff to the north, the long stringer reports were embedded squall line type tornadoes, and everything to the east was way after dark, middle of the night, early morning hours. So again, just the number of tornadoes by itself doesn't tell you how a day is going to look the way I characterize it. But if you were chasing, you wanted to be in the blue circle, not everywhere else. And then here's just one final example. This is just meant to illustrate the false alarm. There's the event that was in Indiana, Ohio back in August of 2016. That's in this sample. Why didn't I count Kansas City? Again, it's a false alarm. I didn't count it because I don't know uniquely how many, I don't even know if that specific forecast was for supercell tornadoes during daylight. So without knowing that, there's no way to deal with false alarms. All right, so here's a table. This is the summary of the whole thing. To get oriented, the first column is my assessment of the number of grid hour events. You notice I put words in parentheses like isolated, multiple, and big day. This is entirely subjective on my part. There's nothing that these mean, but the isolated just means there was like 1 or 2 grid hours of tornado. It could have been literally one storm for 10 minutes. It could have been 1 or 2, but it's not a long duration. It's not widespread at all. There's really one chase target. That's all you would have. And then on the columns we would have, if this works, so 0% is the SPC forecast did not have tornado probabilities where the tornado occurred. So the way you'd interpret this is to say, okay, if there was a single tornadic storm for less than an hour and we didn't have tornado probabilities. 116 of the 126 events were a single storm within 1 hour. So that means we're not, and we're, the big days, okay, there was one that for some reason, I don't remember the details of that specific event. But generally, if we don't forecast it, it tends to be isolated if it happens. So if you go across this, you look at 2%, if you look across this row, the most common forecast for isolated daytime tornadic supercells is a 2% tornado for the whole country, all 8 of those regions added together. The most common 5% outcome is multiple tornadic storms, or multiple hours with at least 3 or more grid hours of tornado. And then as you would hope as a forecaster, if we're like any good at all, you would kind of hope that these get bigger like this, that the most common outcome with 10% or greater, and I lumped high risk and moderate risk in there too. The samples are just too small to look at them by them, because this is only 6 years. They were not exactly the greatest 6 years in tornado history. So I just looked at, basically if it's a 10% or greater tornado, that's a big day forecast. So, and you can look down here, that 669 total. So that's how many hours of chasing, I guess, is a way to interpret that across the CONUS. If you are insane and you don't work and you're independently wealthy and I don't know what kind of Learjet you have, that's about the number of hours you could conceivably chase during daylight that has supercells that produce tornadoes, if you have 0% false alarm. So that's still a lot of chasing. Okay, if you just want to convert these to percentages, it's the same setup in the table. If there's a tornado occurs on a 0% day, 92% chance that it's just an isolated single event. And then of course you go over here, as you get to the 5 and the 10%, there's much more spread, and it gets, the probabilities that it's a bigger event get higher. So that just shows you there's some skill in these tornado forecasts, even for just daylight supercell events. All right, the probabilities in the region. So I'll give you a second to get oriented here. The little abbreviations is the same thing on the map. The Western Plains ones are all clumped together on the left side, and then the Eastern ones are clumped together on the right side. And then down on the bottom, you see there's the seasons. The blue is winter. There's not that many that occur, like open warm sector or tornadic supercells in the winter are not terrible, especially with no tornado probabilities. They're very rare. And then you have the spring in red, summer in yellow, fall in brown. So I'm going to keep the same color scheme and the same organization to the next few plots. So if you just look at this, if we don't forecast tornadoes, the most common time of year for us to miss them is in the summer, the yellow bars, in virtually every region. It's the summer's the most common time for that to happen. And these are converted to number of days per year, the average. So roughly 1 to 2 or 2.5 days per year is how often this happens. So if you're gonna sit around, you wanna say, I'm gonna burn the SPC, I'm gonna get those clowns. I'm gonna show them that I've got what it takes and they don't. You get on average in these regions 2 times a year to prove it, where there's no tornado forecast, and it's with a supercell. So I'm gonna issue the challenge. I wanna hear from y'all when this happens next, and it will happen. When we don't forecast it, but I want proof, not this, yeah, I claim I saw something. I want video, I want clear, undisputable video evidence of a tornado. And not, I heard this from someone else, but let's see if anybody takes me up on it. So again, it's primarily summer, not so much spring, and then it's very rare in the fall and the winter, the dark brown and the blue. Now, if we jump to 2% tornado, you notice the distribution changes a little bit. The Southern Plains comes up a lot more in the spring, so there's more low tornado probability days in the spring, but still the Midwest summer is the most common at roughly 4 or 5 days a year that comes up. The East, fairly common to see that in the summer, and now you're starting to see the high plains and the central, northern, and high plains start to show up as we get to higher tornado probabilities, mainly as you get into the warm season. Now, if we continue this to the common 5%, so if you remember, the most common tornado forecasts were 5% and 2. Those are the 2 most common single forecasts when tornadoes occur. Now the Southern Plains spring, this is why everybody flocks to somewhere within a state of Oklahoma during April and May, because this is the most common area for the typical 5%. Those are the days that we would get tornado watches and things would be most common. But the Midwest, fair number in the summer, it's only like a day less, and then even the Southeast, there's a fair number. And you notice there are more there's more of a tendency for higher tornado probabilities in the southeast than there are in the rest of the country, because they're skewed to the more obvious scenarios. As we show, as we get to the 10% or greater forecasts, again, southern plains dominate this along with the southeast. In the rest of the regions, it's maybe a time or so per year, but you get 4 or 5 days per year. So this is a reflection of why people chase the central and southern plains during the spring. I mean, I don't have to tell you all that, but it just shows that the forecasts actually match tornado climatology to a reasonable extent. All right, so we can do the same thing. Now, I'll give you a second to orient to the color scheme here. These are the SPC Outlook contour colors. The only thing that's different is this dark gray. I gave it a blah color. That's when we don't have any probabilities. So that would be the 0. 2 is green, 5 is brown, 10 is yellow, 10 or greater. So this is what it would look like on the webpage, the tornado contours. If you notice in the winter, there weren't very many events. There's only a couple per winter that occur. They tend to dominate in the southeast. Now you may ask, like, golly, what is this with the Ohio Valley? Why are almost half of all the events? That's only 2 events. So it's like nearly 50% of 2. It doesn't really tell you much. So it's a small sample. And obviously people aren't, I hope they're not driving around the high plains and the northern plains in the winter storm chasing. I mean, maybe it works nowadays, but maybe this year it did, I don't know. But in general, you're not gonna be very successful. All right, so if we move to the spring tornado days, this is where the southern plains jumps up quite a bit. The most frequent 2, 5, and 10% tornado forecasts are for just the Texas-Oklahoma area. And again, that verify with tornadoes. So you could say, well, y'all are just biased just because you're in Oklahoma. So it's like, no, these are the ones that tornadoes actually occur in them. So, but the other area that roughly keeps pace is the southeast, that area Arkansas over to roughly Georgia, which is actually a bigger area than just Texas and Oklahoma combined. So you can see that, it depends on the time of year and the region, the season. It makes a difference in how the forecasts turn out. And of course, we go to summer. If you want a big day, you either need to be a modestly high forecast. 5 tours is most common in the Midwest. 10 tours is actually the high plains. But there's not a lot of them. It's just when they occur. They tend to be in the Midwest or the high plains, and now the poor southern plains have dropped out. It's sad. People gave up on us. This does include June, so it cuts off pretty quick down here. And then we go to the fall. Anyone have any guess why the east and the southeast jump up so much? I'll quiz y'all. What would be a reason? Tropical cyclones would be one. Anything else? Do you remember what I used this fall? September, October, November? Is it possible there's 2 regimes that are captured by the same season? Second season. Yeah, it's the November stuff. You start getting into the more synoptic outbreak type stuff in November, and it's the hurricanes in September. Yeah.
You also have less dynamic forcing or less dynamic forcing because it's a transition season.
Well, usually that would mean more because they're more baroclinic dynamic systems, but yeah, there's a whole bunch that goes in. It's a tricky season, the fall, because it doesn't really, there's not one unique thing that happens. There's a couple of different things that tend to happen. Okay, so for chasers, this is probably the money graph. This one, now, don't ask me to reproduce what I called photogenic. You know what that did? It was I got on my Facebook feed, I typed the date, and I said, can I find any one of you clowns that came up with a picture that looked cool to me? Some of them I knew, some of them I didn't. So this is what does SPC forecast when photogenic daytime tornadoes occur. I think there's I counted 117 of these or whatever. I don't know if I have the number. I didn't put the numbers, but I put the percentages. So anyone who says SPC stinks, 10 and 5 Tor are the 2 most common forecasts when pretty tornadoes occur. So if you don't get the pictures, that's not my fault in the forecast, it's you. Only 7% of all the photogenic tornadoes, again, this wasn't scientific. I just look, if I did a search of a day and I couldn't find anything, it wasn't photogenic. I had to see direct proof that, wow, those are cool pictures. Somebody had to show me something. And some of them were obvious, and I actually got the fortune of chasing them. So anyway, there's this information. Does anybody have any questions on this part? This is sort of because y'all are the first people in the world that have ever seen this breakdown. I didn't even show my coworkers before I came here. Partly because I forgot, but that's And the ones I was working with don't chase, so they didn't really care. But any questions on SPC outlooks related to chasing? Or are there any of your preconceived notions that are now destroyed? Or did I reinforce what you thought? Uh-oh. Well, we'll soldier on. So I guess no comments. Now, that means I'm not going to see anything on social media, right? I'm not going to see any comments right after this presentation about, let me say this, if I was with one of those forecasters, I'd give them a piece of my mind. I'm right here. Anyway, I just thought it'd be interesting to see this, and honestly, I didn't know what the results would look like myself, so if anyone's interested, I can try to share it's just a simple PowerPoint. I can put it on, share it with you with Google Drive or something. If someone wants to look at this in more detail, I know like 10 minutes there's an awful lot to absorb here. Now here's one more thing that's related to chasing in that database, but it's not really talked about. This is using the same database, it's the right-moving supercell tornadoes since 2003 versus QLCS tornadoes. Same people doing the storm assessment. So this isn't just like, oh, well, people suddenly decided to call everything squall line when it wasn't. No, this is the same people made these convective mode assignments. If you've sensed that there are fewer good chase storms than there were 10 years ago, it's dropped by about 30 to 40% across the CONUS. If you get the sense that there are more squall line tornadoes, like on December 15th with like 120 reports, whatever craziness that was, QLCS tornadoes have about doubled in the last 10 years. Now, whether this is a longer term trend or if it's just a short term variation in weather patterns, I couldn't tell you. But it makes for it very difficult as a tornado forecaster to figure out what to do with this. The total number of tornadoes isn't changing nearly as much as the types of storms that are producing them. But it makes a big difference in terms of damage potential. So again, if any comments, questions on this stuff, because I'm about to change gears. Yeah. Normally, the question was, are the data skewed to, because there's more people out there? That's probably part of it, but most of them are occurring at night. And for whatever reason, there's a tendency for more of these reports to be at night. Now, I can speculate. This is just me speculating. So this isn't, I can't prove this, and if we go to court, I'm going to deny it. But I think it's way easier to call something a tornado when no one saw it, and weak tornadoes leave damage that is virtually indistinguishable from straight line wind damage. And if you have like a mesovortex, a little swirly in a squall line, and the winds are not severe along most of the squall line, but they are just on the right side of a little vortex, and that's the only place where the winds are strong enough to produce damage, guess what it's going to look like? A little stripe of damage. Are those all tornadoes? I seriously doubt. There's some fraction of them. I can't prove what it is, but to me it could be 25 to 50% of these might not be actual tornadoes. So if people are warning for them, they're going to be more prone to call it a tornado when they do a survey, because you just can't tell the convergence signatures that are typical of stronger tornadoes. Weak tornadoes don't really look that much different. There's just a couple of trees down, and you say, well, I guess it was a tornado. And I'm not saying people are trying to do this on purpose. I'm just saying that we just don't know. We don't have the evidence that we have for like the supercell tornadoes. In the past, it was the sheriff-nado, the hallucinado, that stuff out in the plains was common for EF0s, but I think we're getting something similar with the QLCS tornadoes.
One quick question. So do you have any, maybe small semblance of an idea of why there seems to have been such a large reduction in supercellular right-moving thunderstorms over the last 20 years?
Short answer is no. I just think that we just have there haven't been as many favorable patterns. I mean, if you take the plains area, years like 2014, 2018 were both incredibly slow, other than a couple of tornadoes in Nebraska. Overall, those were very slow years until you got way into June. And I think that it's just the background patterns. For whatever reason, we have been fluctuating, whether it's the large scale El Nino, La Nina cycles, whatever decadal oscillation you want to come up with. we just haven't had the Four Corners trough as frequently through the meat of spring in some of these years. What's driving that is anybody's guess. And I started cutting my teeth chasing in the mid to late 80s. Y'all have no idea how bad that was. I mean, there were like 8 tornadoes in Texas, Kansas, and Oklahoma combined in April and May or something like that. I mean, it was insanely bad. People would be jumping off cliffs now. Oh my God, there's no tornadoes. What am I going to do? And that was when I learned to chase, was like, wow, it didn't thunder at Oklahoma City in April of '88. That's pretty sad. Not even one time did it thunder in that month. So, yeah, there's a lot of stuff that we just don't know, and that's probably my best response. I'm not sure.
Hi, I was wondering if you could comment, just looking at the data, just eyeballing it, every time there's a spike in QLCS tornadoes, there seems to be a spike in right-moving supercell tornadoes. But one year in particular seems to be 2013, when there's a slight spike in QLCS tornadoes, and there's a deep spike in the right-moving supercell tornadoes. So I was wondering if you could maybe comment on why that could have been, with any data that you could have seen.
Well, now here, if you look at it, okay, the peak, in the earlier peak, this actually should be 2011, so that was a big tornado season. Those peaks maxima should line up. I'm skewed off to the side, but I'm pretty sure it was 2011. The 2013, there was a big dip. Supercell tornadoes were down, but there was a little bit of a spike in QLCS. Some of this comes down to single events. I mean, like the December 15th event in Iowa. I mean, if I heard right, their survey, the final number is like 120 tornadoes with a squall line. People saw like 3 or 4 tornadoes. Can you imagine that with supercells? There's 120 tornadoes during the day. Oh, but we only saw like 3 of them. Really? I mean, they're coming, cornfields are great with leaving debris tracers or something like that. There's a whole bunch of really high-res satellite imagery right after the fact. I'm not saying what the forecast offices are doing is wrong or dishonest. I'm just saying I don't know if what they're identifying are really what we call tornadoes. So one spike, 120, is more than we used to get in the entire year for the entire United States. And that was in like 6 hours one afternoon. When you have events like that, which are becoming more common with 40, 50, 60 tornado reports with squall lines, that just wasn't the way it was when my career started. So I think some of it's reporting, some of it's warning, and some of it's wishful thinking, and how you weight all that, I don't know. All right, I better get moving on, because we got some more stuff. I might be nice and skip the thing at the end where I'm going to quiz y'all, but. Okay, so what I want to do here is there's been a lot of talk of radar stuff, and I thought, I've done a little work on the tornado intensity estimates with radar, so how about we look at that? And especially there was a whole bunch of chatter about the strongest rotational velocity ever measured with the Mayfield storm. But I'm almost certain that everybody that spoke up about that did not look at any scan either side of that one. They said, oh, look at this one. Well, I'm going to show you the sequence of scans, and you tell me what you do with these data. Okay, so things that you have to consider if you're estimating tornado intensity in real time. Quality of the velocity data. You have to know what side lobe contamination is. You have to know when you have high confidence radial velocities and when you have low confidence. Are you sampling near the ground? How long do these signatures persist? What does the near storm environment look like? Does it favor stronger or weaker tornadoes? And what's it encountering? So what should I expect to see? All right, so I'm not going to spend too much time on this. I've got a table. This is some published stuff from Brian Smith and myself at SPC. Basically, the whole point is as the storm environments get more dangerous and rotational velocity increases and you encounter more stuff, the probability of high-end, like EF3, 4 plus type outcomes increases dramatically. So we can do this, and these are based on samples of thousands of storms. So this isn't just like, hey, I looked at that one and now I'm an expert. No, we've looked at thousands and thousands of data points to get this. So another way to look at that chart is to put it in a 2-dimensional plot. Basically, low STP, and is STP the perfect way to reflect the environment? No, but it's easy. It's a single value. So VROT increases, rotational velocity on the X or the Y-axis, and then STP, some measure of how dangerous is the environment. So if you get in the upper right is where the scary part is. And the reason this is hatched, that would be the purple, that's where you know something about the population density makes a big difference in the outcome. Intense signatures in dangerous environments going through open country don't result in high-rated tornadoes until the rare case they hit something. But if this is going through more, right down the street, different story. Okay, so duration of the signatures makes a big difference. The group of these are just, think of these as a summary of a scatter plot. Basically this box, the shaded box, is half of the data, fits inside the box, is in that range. These are shorter lived, or these are, from 1 to 5 minutes, 6 to 15, and then greater than 15-minute duration, but in purely open country. The entire tornado path had low population density the entire time. So you see there's a lot of spread in the outcomes. Sometimes you're getting things rated EF1, the same signatures hit stuff, and it's EF4. So there's a lot of spread in these, but when you encounter at least part of the path, and the magenta plots has modest population density, and it goes on longer. Look at these. The sample's not very big, but if you have 15 minutes of 70 knot plus VROT, and there's people in the way, almost no chance that it's not a violent tornado. So this is where Mayfield would fit into this category. Now, whether it's EF5 and whether that even matters, I don't know. The point is, we can't tell the difference in real time, slicing a bologna that thin. All right, now let's look at the actual Mayfield case. This is GR2, so it should look familiar. I've just done a 4-panel. And what we're gonna do is I've locked the screen so that we're not jumping around, but here's the couplet with the tornado down here in the lower left. There's your, probably some reflection of lofted debris and the high reflectivity. There's a correlation coefficient in min that's coincident with that. People, when I say velocity quality, look at the little triangle. That's all in the inflow region of the storm. It's low reflectivity. You have a lot of wildly varying velocities, and the strongest inbounds are here. You can come up with some erroneously high rotational velocities if you don't pay attention to where the data are located with respect to the storm. The actual couplet that matters is this down here, which is right there in the ball of the hook. So that with big tornadoes, that's the way it's gonna look almost every time. So this one has a rotational velocity of 86.5 for that scan is the way we calculated it. That's high end. So that you could get, just for example, the Moore tornado that was sampled similar way was like in the low 90s that produced $2 billion just right down in damage right down the street. Okay, next scan. This is a pretty clean one right there in the hook. Again, the triangle gives you a reference point. Rotational velocity is almost 90 knots. Again, this is very high end. This would clearly be a dangerous storm. There's lofted debris several thousand feet in the air. These are all just the base elevation cuts. And we're looking from the radar to the south. This is after Paducah went down. So we're looking at the Fort Campbell radar, which is down closer to the Tennessee-Kentucky border, but similar distance away. All right, now here's the scan where everybody's losing it. Oh my gosh, it's the worst VROT ever. 132.5. Is there anything potentially questionable about this scan? I know it's maybe a little harder to see it in a big room like that. Does anyone see anything that you might wonder about? Yeah.
The pixels do not match up with the surrounding pixels on some of the inbound velocities.
The inbounds. So the mention is the inbounds. Yes, there are some 100 knot plus inbounds. These are 100 knot plus outbounds. That looks somewhat reasonable. It's a somewhat normal looking display of the outbounds, and it's within the the area where there's some lofted debris. But this particular radial, these velocities increase dramatically, and there's like one gate that's like 130, 140 knot inbound. One single gate in there. Now, there's probably lofted debris, the real high reflectivity and all this, but look at the very next scan. These are just a couple of minutes apart. VROT's back to 89. Now, you tell me what's realistic. 86, 80, about 90, 132, 89. What's the outlier? It's the crazy scan. So if you want to insist that that's the greatest VROT ever, no, it's not. For questionable data. This is El Reno. When we don't pay any attention, there's one of these gates inbound 194 knots. The pattern looks a bit unusual looking at a lot of tornadoes, so we didn't use that value. That's a high estimate, but if you just take it at face value, the VROT's 149, case closed. This is the strongest signature in the 88D era. So people have very short memories. Especially anyone around here was going along with that, that's who I'll slap. because this is right down the road from here. So anyway, just be careful. It's real easy to just say, this has to be violent. This has got to be EF5. And everyone's getting on Tim's case. As he mentioned, he doesn't actually do the rating. He advises the people that decide the rating. And there's other people that know how to look at this stuff too. So just be measured in your responses on these things, because unless literally your livelihood depends on being the first person to say the stupidest thing possible, just take a deep breath. There will be another scan update within a minute or two. If it's consistent, then maybe you're onto something. So that's my plea to you. And so if I see you on any of my feeds doing that, I'm coming after you. And if you're right, I'm not going to, but if it's this stuff, like, I've never seen anything like this. It's like you've looked at 5 radar images. So, okay. I've looked at tens of thousands. It's not that I'm the world's most amazing radar person. It's just I've looked at way too many of these images. All right, so any questions on the radar stuff? Hopefully none there. I'd like to move on to we'll do forecast stuff. I have to show at least one forecast case. Of course, it's one where something interesting happened for me and for a couple of people here. So it's the May 16th. I call it the Sudan, Texas tornado. Other people call it the Earth. I don't know why. I haven't measured which town's closer to it. I guess that was the direction I was looking from. So I call it it's my presentation, so it's the Sudan, Texas tornado from May 16th. So I'm just going to show some of the stuff that I typically would look at. And of course, I'm skewed to SPC stuff because I've helped develop some of it. This is just focusing on some of the environmental information from the HREF that was available in the morning, and the 2% tornado contour from the actual SPC Outlook is on there. So this is one, everybody tends to have these great glowing memories of an event. Oh yeah, it looked great before I went out and all that. Look, the flow's forecast to be 25 knots. That's hardly a banner flow regime for mid-May in the southern high plains. But and then we go to the low levels, forecast for 18Z, 10 knot south winds at 850. Okay, so the shear profiles are hardly awesome. And so anyone wants to convince themselves, oh yeah, I knew this was gonna happen. Good, come work with me. Please tell me how to do my job better. I'd love to learn from you. Okay, so we go to the forecast for 0Z. So 6 hours later, the forecast, again, there hasn't been a substantial change, still 25 knot type winds, if you can see those. Maybe this sorriest hint of some kind of speed max that's already over North Texas. I mean, I don't even know if I believe that. And then 850, okay, maybe the winds have increased to 15 knots. So this is a marginal looking supercell profile. If we need to convince ourselves anything else, here's the dew point forecast. I don't remember what time I did this one, 23Z, so I'm not showing every time for all of them. Dew points ranging from roughly 50 in the western panhandle to 60 as you get into northwest Texas. So these are mostly mid to upper 50 type dew points, are forecast for that evening in the area where you might expect storms to develop. And temperatures are forecast to be around 80. So what do you get for temperature dew point spreads? 25 degrees, 23, somewhere between 20 and 25 degrees. So that's marginal. Again, it's consistent with the wind profile. We look at some like forecasts for storm relative helicity, or so, I think that's what this one is. Rather modest value. I mean, the green is just 100. I mean, this is 0 to 3 kilometers. That's not big. It gets way higher than that. So modest low-level shear, buoyancy. I mean, 1,500. I don't know, if you're lucky, you could eke out 1,500 to 2,000 Cape, somewhere in there. Again, is that huge by Texas South Plains standards in mid-May? That's probably 50% or 75% of a typical chase day. So the Cape's not impressive, the moisture's not, the shear's not. If you knew there were going to be tornadoes, then again, you're a better forecaster than I am. But typical diurnal thing, there is a forecast. It's a choppy pattern, but some increase in the shear as you go into the evening as we get to 8 o'clock local time. And you get the buoyancy, whatever noses up in there. So there's some things, and you notice the updraft helicity is also plotted. Look at all these splotches everywhere. How on earth do you target something in that? There's like target what? There's like 10 different possibilities. And in Southwest Texas, who I was saying, just show I'm not biased. It was, look, you could be down here in Fort Stockton having a good old time. So point is, other than, in this case, the SPC forecast actually might help you sort of narrow it down. It's not always the case, but on this day it might help a little bit. Okay, so we put the other plot. Hopefully some of these look familiar. These are all publicly available on our webpage. This is sort of the composite of the updraft helicity tracks with all of the individual convection line models that go into the sample. Again, you don't see a lot of long paths. There's a little longer, this Fort Stockton thing. There's something down there, maybe Brownfield. And then there's a couple other splotchy stuff. How on earth do you look at that and tell me, oh, I know where to target in Texas? Which of the 10 possible storms are you talking about? And for why? So the point is, there's always going to be a factor of luck involved in this. And on this day, I'm going to admit straight up, there was a lot of luck involved. And again, the forecast for later, that was a previous run. Now here's the newer run. I mean, there's maybe some consistency, but remember, there's also a time lag member in here. So some of the members are from the previous forecast, so they should look the same. Point is, there's kind of a smattering of possible supercell paths. None of them are terribly long-lived, and nothing looks that impressive. Okay, let's jump into some of the real data. Around this time, what ends up being the storm of interest is this one. It's not the Warren storms. All of these, there's actually an old outflow boundary that's sagging southwestward up here. It had been raining more up in Oklahoma earlier. So these storms have some weak supercell structure. They have the higher echo tops. They've got the larger hail signatures, and they're the ones with the warnings on them. The only one that really has decent cyclonic shear is pretty high up, is the one up closer to Amarillo. So again, you have to know something else other than this to know why would I be messing around with these storms? Because this boundary is undercutting these storms. They're basically moving southeast and the boundary is moving southwest, so they're staying on the cold side. And it's, temperatures drop into the low 70s. That's pretty cool for northwest Texas in May. All right, so we just move forward. You see the storms, they're moving along. Maybe you're getting some slow intensification. Then finally a warning pops up down here, and this ends up being the storm that we actually intercepted on this day. And again, we were coming in from the southeast, and there wasn't super high confidence. It's like, well, I think the moisture looks a little better here. Anything we can get closer to a 60 dew point is better than 57. And it's like this will stay more isolated, and it's not undercut by the cool air outflow like these storms to the north. All right, so let's zoom in on the storm. This is a 4-panel reflectivity to the top. Now this is looking aloft, velocity, echo top, and the max expected size of hail. So you can see there's broad cyclonic shear. This is looking to the northwest from the Lubbock radar site. Not really much of a classic echo overhang or bounded weak echo region or anything, but there is a 50,000 foot echo top. And so you have evidence of at least what looked like might be a weak supercell. And if we go to the low levels, again, choppy velocity signature, not really too much structure. There's a bit of a core, but nothing jumps out with that. So 0024, turns out the tornado that formed with this is about 38 or 39 Z. So this is 15 minutes before tornado. Maybe you've got some convergence on the rear flank. You're starting to get a hint of an appendage. Echo top has been increasing. Hail signatures holding steady. Again, a little bit, it's still weak cyclonic shear. These are not strong velocities, but more of a bit of a hooked shape. Again, the echo top stays up there. So there's been a big pulse of updraft that has been going on. Now we're starting there's some messy velocities here, but the stuff to the west is actually in the higher reflectivity. So now you're starting to get a little tighter, a little stronger, but this is a rotational velocity of maybe 30 knots. These are not high values. And notice the radar's not in the rapid update scan. You're only getting images every 4 or 5 minutes. So then right around, just in the minute before tornado genesis, there, again, a VROT is maybe 30, 32 knots. That's not anything spectacular, but it does have more of a hook structure. The echo top has come down. And you notice the tornado, the warning is up here. The tornado is actually going to be way on the edge of the warning because it's with the tip of the appendage of the storm. And then by the time the next radar updates, the tornado's over. So you had literally one scan that really said, hey, well, maybe. And perhaps the one before that. But a lot of this is you just have to look at the evolution of it. And now the question is, I hope you're not out in the field just with your eyeballs buried in your laptop looking at, radar scope or whatever, or the Omega, whatever the other one is. The point is, there's a reason you should be using your eyeballs. So what I've done is I've time matched the radar, just the base velocity or the storm relative winds and the reflectivity with the ground view looking at the storm at the same time. So when it didn't have 0020, this is 19 minutes before tornado time. I mean, there's a hint of a low-level updraft. Maybe you can argue it's weak, striated look to it. There's no strong signature. There's weak rotation aloft. Again, not much of a hook, but you can at least see there was a core and there was occasionally some lightning. So we move forward. Again, these are going to be matching every radar scan, the closest pictures I had. Again, there's sign of an updraft, this drawing in this moistened air right off the edge of the core. Typically that's how you see wall clouds form. But again, nothing that just says, oh, well, I'm certain there's going to be a tornado. But somewhere in here you start getting interested. And notice the radar hasn't given you that yet. Now we get to 0028, and we're now 11 minutes from tornado genesis. We're starting to get weak rotation in that hook. A little bit more of what you would call a typical wall cloud, and maybe even a hint of an inflow tail, a bit of a tilted updraft over this. Again, looking northwest right here. This is several miles away from it. So at that point, at least we were smart for once. I don't know, a lot of times I'm dumb and I wouldn't do anything. But on this day, for whatever reason, we were smarter and we said, we didn't expect a tornado today, but I said, I'm telling you there's a chance. I'm not sure why, but it looks like this one might try to produce something. And another interesting aspect of a day like this is, does anyone remember what happened in Texas a lot last year prior to these string of storm days? What was going on in Texas almost day after day after day? Storms everywhere. No haze. It's not the best moisture in the world, but the haze has been scoured out, so the visibility is outstanding. All right, so we just said, hey, if it's going to produce one, this ought to be photogenic. Well, let's just move in closer. Now, and other people stayed back and had great views. So really, you couldn't do anything wrong with this if you were within like 10, 20 miles of it. So now you're getting this much more obvious sense now that the rotation has increased, this striated look to the updraft. That's actually the very beginnings of the tornado here, and a little hint of a clear slide. Again, what looks like a hook on radar, you can see right through it. It's just a few big raindrops. And then we continue moving forward. This is right near tornado genesis. Now it's pretty obvious that, I guess I wonder what that thing is. And and that's about like a mile or so due to our northwest. And then this just moves across, and this, again, I think it was within a mile of us. And all of these images are between those radar images. So the entire tornado occurred between. These are all like a minute apart. So, it was nice and pretty, and I didn't do anything. These are just straight off the camera. So, there are other people that have very similar images from all kinds of angles. And, it had a really cool rope out. If you look in detail, if you can see that, it was very convoluted, and it couldn't have been 10 feet wide. So you're not going to resolve this stuff with the 88D from 50 miles away. There's just no way. And then we come later, and we've lost the strong rotation. You've got a much more classic supercell structure, no more tornadoes. So the whole point here is that if you want to get better at this, get good at that's why I tried to put the radar with it in the images so you can see what it looks like at the same time what the radar looks like. Try to do that in your head to match these up. What do I think? Or look at the radar. What do I think this should look like? Or I'm looking at the storm. What do I think the radar should look like? And you'll get a lot better at interpreting both. All right. I'll go through this last one real quick. This is going to be your quiz. We'll see if you pass or fail meteorology. And simple task. You have to tell me if the soundings I show, I've got maybe like 8 of them, is this an EF3 plus tornado within 100 miles and 2 hours of it or not? Now, first you got to tell me, was this an EF3 tornado? No. It was the middle of nowhere in the Panhandle. Yeah, there's nothing to hit, so we don't know. But the official rating was EF2. So I may be trying to fool you on some of these on purpose, but okay, so you tell me. Everyone yell it out. Is this EF2 or EF3 plus or not within 100 miles and 2 hours of this sounding? This is a lot harder to do when you don't know the answers. And I purposely blocked. You're not going to know that. Unless you're like some savant, you're not going to know what day most of these are. Okay, so we're going to give like 5 more seconds. Somebody blurt it out, yes or no? Yes. Is there a consensus? That sounded like 50-50 to me. The answer is no. This is the 0Z Norman sounding from May 20th of 2019. It's a pretty scary profile. There was no tornadic storm anywhere near the Rayop. Okay, what about this one? Big tornado or not? So yes, sounds. I hear more yeses than nos. You fail. This is the 0Z Jacksonville, Florida sounding from January 23rd of 2017, the high risk down in Georgia. These storms struggled to produce tornadoes in southeast Georgia, and that's what the profile looked like. So again, anytime you say this is easy and it always works this way, good luck. All right, what about this one? The only thing I'll tell you is it's not in the southeast, but is EF3 plus or not? Are these random guesses, or do we think that, I mean, you got a 50% chance. Yeah, well, but that doesn't mean anything. Oh, good, I've got you set up perfect. If you think 2 in a row is all it takes. This is the sounding from that 2% tornado graphic I showed, the Dodge City sounding from the Mineola, Kansas tornado, the same day as the tornadoes up in southwest Nebraska. So this is, yes, this was well within the time and spatial constraints. What about this one? Yes or no? It's, okay, now you guys are going to feel bad. It sounds like a roughly 50-50 split. This is the super outbreak sounding from Birmingham. There were way more than one. There were a dozen EF3 plus tornadoes within the criteria for this sounding. So what about this one? Is it a trick or not? What is it? Yes or no? Yes? Are you just trying, is this like you're trying to use reverse psychology? It's like, well, this one looks worse, so it probably is. Yes, it is. And I don't know if, I'm trying to remember which day that was. It'll come to me later. What about this one? Yes or no? Sounds like the no's are winning. The no's lose, EF4. This was one of the early morning tornadoes at the end of the Easter 2020 outbreak. This is Charleston, South Carolina. There was a tremendous radar signature with this, a 90-something rotational velocity of 20-something thousand foot deep TDS. So it very much happened. What about this one? Definite yes. Okay, it sounds like more yeses. Okay, good. Y'all are getting the hang of this. What about this one? No, and I don't know isn't a forecast. It's like the no. Probably. Oh gosh, which one? I'm having trouble remembering which one's which. I'll get that. I'll let y'all know. What about this one? Yay or nay? There's a little bit of missing data, but just look at the shape of the profile's accurate. Yes or no? Gotta hurry. Forecast pressure. It's due in 3, 2, 1. Yes. This is maybe a very 5149. Yes. No storms. That's an Oklahoma City. That's a Norman sounding. What about this one? Forecast clock is ticking. 3, 2. May 3rd, 99 EF5. Right down the road. And what about this one? Why yes? Why on this one? Okay, so the you're saying because it's got the nice loopy hodograph. Anyone agree? Is that good enough? Well, I mean, if you had chased, you would have agreed. This was near Amarillo, like sometime in mid-April 2017, just Castro County. It's somewhere southwest of Amarillo. It's like a 3/4 mile wide EF3. And then I think this is the last one. Yay or nay? Okay, so I kind of cheated, but the answer is no. This is the Little Rock 0Z 11 December 2021 sounding. It was too far northeast and too much after this, so it does not count. So anyway, hopefully you guys will at least think about this, that it's not as easy, these quick judgments don't work. So. All right, I'm sure everybody's had enough. If y'all can send me email questions on the side, because I don't want to keep it, and plus I got to get up at 6:30 in the morning anyway, so I've had enough. So again, thank you everyone. It's been fun.